recording now.
So yeah, I think this meeting, I have a lot of ideas for this, for all the different areas of research that we could go down. But I think the best way we can do it is by just having a conversation about each one. I even have like a pad here that we can draw on to
Thank you.
kind of play with ideas. Yeah, I'm inspired by Gabriel's methods.
Do you have a pen, or are you still?
I'm using a mouse still, unfortunately.
Yeah.
Let me go back here.
I like your manifolds, Dennis.
Oh, thank you. This, yeah, it's not me. I mean, it's a good artist. There should be more mathematical art, right?
That's true.
Felt like
there
it was hard to find.
Art.
Yeah.
There's like MC Escher, and that's mostly it.
Yeah, Escher, and not many after him.
With actual actual static ideas, you know, with mathematics.
Yeah.
Not just like,
actually, this the presentation you gave, Gabriel, about Karatani kind of linked this idea of mathematics, aesthetics, and let's say like education as a triad. I think. But yeah, I don't know. Maybe we can go into that because
you know that
it's so hard to evoke these ideas if you don't have a lot of training in the formalism, right?
I think that Barry Mazur's book on imaginary numbers is a really good kind of example of how it can be done. It's really crazy the way that he.
Yeah, he's like one of the great expositors.
Yeah. I think it's called
complex analysis is gorgeous.
I think the book's called the square root of -15.
Oh, he has one just called he has one called Imagining Numbers.
Yeah, I think that's the one. Imagining Numbers, and then the subtitle something like the square root of -15. It's really interesting because he tries to.
Oh yeah.
He tries to make comparisons between the sort of intuition you need to work through a very complex imagery in a poem and things like this, and certain parts of a proof.
Yeah, in a lot of ways, Badiou's theory is a kind of a meta theory on math as well, because right, like math is its own world, but the way we try to understand it, the examples we use, it's a totally different world, right? It's a world that is conditioned by what makes sense to us, it's informed by like our concerns, right? Of, for example, this presentation, right? I can't just present a lot of math without any context. I have to make connections between this and like our concerns with explicating Badiou's framework. So in that sense, yeah, I think there's something to be said about Badiou and education of math, or math education. Yeah. But yeah, so let's get started. So these are all the topics, right? There's a lot of stuff. I try to make it as step-by-step as possible so that every topic kind of builds on the previous ones. But just know that this is like one path through these topics and not necessarily the standard one. And I wanted to start with the idea of pictures of structure. So we, as philosophers, we have this specific idea of what structure is, right? Which is informed by like structuralism as this idea started in like French philosophy, and there's this formalism and so on that kind of is borrowed from mathematical thinking in a way, but I wanted to, in some sense, Badiou is like a return in the other direction, right? Taking ideas out of the French context and going back to math. it's a return to math. So so I want to have that context when we talk about pictures of structure. In some sense, this is larger than just the examples of mathematical structures. But if we want to have a good idea of what structure is, I think we really need to understand how it is depicted mathematically, right? So structure, in other words, structure in general can only be clear when we talk about mathematical structure. So what is a picture of structure? So the first example of that is a morphism, right? The most general example. And these diagrams, this diagram on the right here shows a very simple example of how morphisms can relate to each other. So the one we're most familiar with is the function in set theory, right? A function takes points in some set and maps them to other points. It's pretty simple, right? But this is still like an intrinsic view of structure. It assumes that the structure is somehow inside of a thing. We call it a set. But the math that we need to get to in this presentation and in our understanding of Badiou in general is an extrinsic view of structure. We want to be able to treat these morphisms in terms of their behavior along with other morphisms. So in some sense, this picture with the colors and the dots and the sets, we need to translate that into the top picture, the one with just diagrams, right? So we're kind of making this journey from an intrinsic view to an extrinsic view. So yeah, just as a review, we have this idea of a domain and a codomain for every morphism. So that's the starting set and the ending set in case of sets. And then we can form morphisms by composing other morphisms, assuming that the codomain of one lines up with the domain of the other. Okay, so this is a general way that we connect these things together. And then, yeah, I added a question here, like how many different morphisms exist between two sets, just to give you a sense of the size of things we're dealing with here, right? Yeah, so a nice way to think about this is, what if the codomain set is has only one thing, it's a singleton, right? Then there's only one way that you can map any set to that singleton, right? It's a constant morphism. And then the case of two, right? If the codomain has two elements, we've already talked about that in other meetings in regards to the transcendental in Badiou's system, which if it's in a classical world, it only has the true and the false, right? And then the question becomes, how many different ways can you map something to true and false, right? So in that sense, it's 2 to the n. We know that because the power set of any set is 2 to the cardinality of that set. So if you have 5 elements, it's 2 to the 5, right? 32, or right? So so let's say that in general, the number of morphisms between any two sets is the cardinality of the codomain raised to the power of the cardinality of the domain, right? So I don't know if that was clear at all. Let's see. So we have some stuff here, right? All the different ways of taking this stuff to 1 is 1 to the n, right? Similarly, if we were to take it to 2 elements, it's 2 to the n, and so on, right? That's how many maps there are.
Mm-hmm.
Okay. So in that sense, we're dealing with already a really large space of things. It's a space of morphisms from one thing to another. And this is not interesting in itself. This only becomes interesting when we start to talk about ways of slicing up this space of morphisms. So when we talk about structure, we can formulate this structure in terms of properties of morphisms. And feel free to jump in if you have any questions, or if you think that this is going too slow or too quick. I just want to get this idea very precise, because the move from this internal picture of structure to the external picture of structure requires that we understand how it is that morphisms themselves can have properties which then constrain the space of between objects. So one constraint we can put on a morphism is to say that it is injective or mono, right? And the aerotheoretic or the category theoretic way of expressing that is to say that if this function or this morphism happens after 2 other morphisms, and it just so happens that this is commutative, then the 2 morphisms on the left are the same, right? In other words, it's cancelable. Also note that this is something that tripped me up a lot and continues to be like a problem sometimes. Like the direction of this composition is opposite to how it's depicted in a diagram, right? So the fact that F is on the right here and on the left here is something that we should keep in mind when you converting between the diagrammatic expression of it and the algebraic expression.
Also another way to think of a monomorphism is as an inclusion, right?
Yes,
that's what that little hook arrow symbol below the set thing means.
Exactly. Yes, and in general, when we move to a generalized set theory, so a set theory that can happen within categories, those inclusions will be our version of subsets, right? There will no longer be a concept of inclusion in the set theoretic way, but we'll have inclusion maps or inclusion morphisms. Okay, so then we have the opposite case, right? Surjective or epimorphisms, which again, if you look at this, the algebraic notation and the diagrammatic notation, and you reflect on that, you'll see the same order of the composition. Mm-hmm. But it means the same thing, right? F is cancelable, except this time on the right. So if just as a clarification, everything on the left, if everything on the left is true, then everything on the right of this implication must be true, right? And then in sets, it looks like this. So the way to interpret this in sets is that a surjective function hits all of the elements of the codomain. It doesn't leave anything out. Whereas for injective, there can be at most one target element in the codomain for every element in the domain, but not necessarily hitting everything. Okay.
Sorry, Dennis, go back to the previous. Can you expand your diagram? I cannot read the notation under the set theoretic diagram. What is that?
Let's see. I don't know if you can expand it further. Is this better?
Not really, but that's okay. You can draw it on your.
Yeah. Let's draw it. So. Yeah, it's saying this, right? And why is this why does it look like this, right? Injective means that for any points here and any points here, I get exactly a corresponding point from left to right. So this is our domain, and this is our codomain. So in that sense, E, right? If this set is E, and this set is X, E is included in X. So we can think about this as like, this is a picture of E in X.
Right.
Right. So the image of this morphism is exactly this. It's a subset of X. So we say, well, many ways to write it, but let's say image of F is a subset of X, right?
And the size of the image of F is going to be the same as the size of E.
Yeah, exactly. Yeah, that's an extra condition.
If it's
Because actually,
yeah.
Actually, yeah, this would be true of any function. So,
Yeah, it's a consequence.
it's constant. Yeah, we need actually it to be exactly the same size as. Yeah, this is the other condition, right? Okay.
Yeah, it's important to remember that categorically the definition of monomorphisms and epimorphisms is literally that like equalizer arrow thing that's left to right cancelable, but like in the context of in the category of set, it ends up being injective and surjective functions, right?
Yeah.
So it's like it's a special case.
Yes. So we're talking about generalization of the set picture into the morphism picture, right? The morphism. We're using the word that Gabriel used in the other day, the resolution, right? If we've zoomed in only to the category of sets, then monos and epis look like this colorful picture. But in general, in the arrow theoretic version, you only care about this diagram, and then this algebra here. And in Badiou's work, everything's informed by I would say Goldblatt, and Goldblatt develops category theory starting from set theory. So everything is referred back to sets, which is why the leap is not so great, and also why there can be a lot of criticisms against Badiou on this point, because he doesn't seem to start with categories in general. He starts with the category of sets and kind of refers everything back to that, right? But Badiou has a good reason for doing that we can talk about later on. Okay, so I'm going to go a little faster through the next parts now that we understand in general morphisms. So there's an identity morphism, which it's basically, you can think of it as a morphism that does nothing. It takes an object to itself. And because of that, it's also left and right cancelable, right? So if you compose the identity with any other function, you get that function back. You have an isomorphism, which is a morphism that has an inverse. So usually that means there's actually two inverses, a left and a right. And those two inverses give you back the various identities of A and B, right? This condition here. This function here has these conditions, right? If it's an isomorphism. And in the category of sets, of course, isomorphisms are just bijective functions. So that can only happen if two sets have the same number of elements, the same cardinality. And Cantor's big revelation was that, the countable and the uncountable, or that there was an uncountable set, right, produced by the power set of the countable infinite. So showing that there is no isomorphism between the two. So yeah, another two things that are important. Endomorphisms are kind of a generalization of identity morphisms. They have the same domain and codomain. And then automorphisms are invertible. And you will see those in the case of groups in mathematics, but also I think you can use like permutations and combinations, like as suggested by this question here. Okay.
And also isomorphism can, right, it looks very different in different categories. Like in the category of topological spaces, isomorphism is really like an invertible homeomorphism, which is like a continual stretching where you're not tearing anything, for example.
Mm-hmm.
It's just important to keep in mind that like these are all emergent from the category you're working in.
Yes, yeah, that's important. So the downside of presenting it this way is that we don't have the richness of examples yet to kind of enhance our understanding of what morphisms are. Like, so in topology, you have a specific kind of morphism, but in like a category of groups, you'll have a different kind of morphism. So each one should be thought of in a different way. And I think that it reflects the notion of structure in those categories, right? What is important? What counts in those categories? That's what gets preserved by the appropriate maps.
Yeah, exactly.
Yeah, and then that's the point of this slide here. So so like we said earlier, there's so many morphisms, even in the category of sets between any two sets. We care less about any specific morphism. We care about classes of morphisms that satisfy some condition, right? Usually there's going to be more than one morphism that will satisfy a property. Like we talk about injectives, right? So in the case of this diagram here, an injective, there can actually be many injective functions. Let me go back to here. So if I have the most basic example here of two sets again, an injective function, or really the only function possible, is something like this, right? Maps this to a point here. But notice that we can actually choose a bunch of these, right? So like that's a function, that's a function, that's a function, right? So there's actually many functions, exactly n, right? Where n is the cardinality of the codomain in the case of singletons. Similarly, you know, if this was 2, right? Yeah, so like I could do this, and I could do satisfying injectivity.
Yeah.
Right, many different choices we can make. So we don't care about any one in particular. We care about the property itself. So in this case, these are all injective. So that's what we mean by a equivalence class of morphism satisfying a condition. And basically the category theory, I would say, in a very speculative sense, it is just figuring out what are the possible classes of morphisms, right? And how do those morphisms change as we apply or remove structure to a mathematical object, right? So like basic stuff is like injective, surjective, okay, but that's very broad. There's other structure that we can now add and remove to narrow down the morphisms that we're working with.
Dennis, can you go back to the slide that you define injective and surjective?
Yep.
If right cancel or even, it satisfies HOF equal to GOF. How do you reconcile this algebraic with the diagram?
Yeah, so the diagram is a commutative diagram, which any commutative diagram means that any path you take in the diagram is equivalent. So that if you read the top, let's maybe jump to here again. Make a new page. So let's see here. So let's take this first one, right? Injective. So that's this, right? Right, and then yeah, F is here. So we write it, the way we write it is, let's think about it as F of G of X, right? So let's call this G and this H, right? F of G of X is equal to F of H of X. This is how we normally see it, right? If not coming at it from a category theory, right? We say we have X, right? X belongs to A. And then we apply a function to it, G. Then we apply a function F, right? And this is the same as saying we're applying H to X and then F to X. So it's F is on the outside. So then that's why we can write it as F of G, like this. Yeah.
But
so that's what this is.
But I think what is, let's say, what is already a hint at a different intuition is that this definition of injective, it extracts the information that something is injective from the relation between two morphisms and not from the relation between a point in a domain and a point in a codomain, right? So you learn something about a certain function from looking how some information is preserved, right, in this commutative diagram. If you move through G to, and then from G to F or from H to F, if those two things are equivalent, right, there is some property to that morphism, which we call injective. You're not defining it based on the points, right?
Exactly.
I think it would help if you drew, for Reza, if you drew the diagram you had before with the injective function in the set, but add some G and H just so he can see how it works, right?
Oh yeah, okay.
Because when, okay, I think you know what I mean.
Yeah, I think I know. So let's say we have A and some elements. Let's make it simple, like 3 elements. And then B is 2 elements here. And then C is another 2 elements here. So then let's say that G would take this approach, right? This is not an injective. This is just composition, right?
Mm-hmm.
So let's say G is this. And then let's say H is this one. Right? Then F takes this approach, let's say. I don't know, is that too dark to see?
No,
yeah. Okay. So let's consider H first, right? What happens in H? Everything in H, H maps everything in A to the first dot here. And then F will take that dot to here. So in other words, the composition of F circle H is equivalent to taking this path. So in other words, it's this, right?
Well, actually, in this circumstance, you're never going to have the equality, right?
Yeah, I'm saying this is not injective. This is just F in general.
Sure.
I mean, well, yeah, actually, F is injective here, but the
no, I'm just saying with the H and G, you're not going to get equality because they never map to the same thing.
Yeah,
exactly. Yeah.
Yeah.
Yeah, I'm just showing the idea of composition.
H and G are not injective because they all map to one point. Is that what you're saying?
Yeah, H and G are non-injective, but F is injective. But how do we see that F is injective? We can only see that if H and G are the same when composed with F. So okay, maybe this is not a good version because this condition needs to hold. Right now, this condition doesn't hold, right? F follow G and is not equal to F follow H because F follow H, let's call this like 1 and 2. F follow H maps everything to 1, right? And F follow G takes everything to 2, right? So they're not equal. But when this condition holds, so when the composition maps to the same thing, then we say that G and H, G must be equal to H if F is injective. So it's an implication, right? F follow G equals F follows H implies G must be equal to H.
If F is injective.
If F is injective. So let's think about it as we start with the only information we have is that F is injective. What can we extract as a consequence from knowing that F is injective? We can extract that if this is true on the left, then G must be equal to H. And this is interesting because we don't know anything about G and H. G and H can be any function whatsoever. But depending on how they behave, when we compose them with F, if they behave the same, then we know they must be equal because F is injective. Right, we know that H must be exactly the same as G. If you think of H and G as different behaviors of a transformation of some kind, in a very general sense, they change, they perform some kind of change, and we don't know what that change is. Well, we can use F to figure it out, right? Because we know F is injective. Yeah, but it's only in this special case when the composition turns out to be equal.
And simply the definition of injective is that everything that is in domain is mapped to a distinct value in the codomain.
Yes, yeah, and so morphisms in general, everything in A must be mapped to something in B. But if it's distinct, like you said, so distinct meaning for any point in A, there can be at most one target. Sorry, for every point in B, there can be at most one target in A. So this is injective. Right? What's not injective is this. Right? That's not injective.
Right. Now, if you in the example you have on the left, you had another dot in B.
Yeah.
Now, is that morphism injective?
Yes, it's still injective.
Still injective. Okay.
Yeah.
So it doesn't have to cover everything in the codomain. It's just
exactly.
Right.
Yeah. So if it did cover everything in the codomain, let's say add another one on the left. This is surjective. So those are two different properties and you can have a morphism that is both injective and surjective. So this is an example of injective and surjective, which, that's why also that this can be inverted, right? Because A and B, now we know A and B have the same cardinality because we have a map that is both injective and surjective. And then that means we can invert it.
Yeah, but I think it really is crucial to see that the difference between approaching it in this way rather than in the set theoretic domain, codomain version of it is that it's a definition of injection where it's all about if a transformation preserves something, right? If it is injective, you know that some information is holding so that you can evaluate these other functions. If they're leading to the same place, then you will be able to know that they're the same, right? Because some information was preserved, right?
Exactly.
In the category set, the definitions are equivalent.
Yeah.
Yeah. In a lot of ways, sets are like the Wittgenstein ladder, right? That you can throw away after you understand it, right? If you're learning category theory, I think most people go by learning through sets because that's what you're familiar with, and it's easy to illustrate like this. But once you understand what's going on, like you don't need the points inside anymore, right? That's the Neo moment, right? When you don't need to dodge bullets.
You don't need to dodge points.
Yeah, you don't need to dodge the points anymore.
Or you could dodge the points.
Yeah. Okay, so that's the idea here. So that in general, morphisms carry some amount of information, and there can be many morphisms that satisfy a particular property. We care about the properties themselves, not individual morphisms. And this last part here is actually a very, concise summary of the Yone lemma, which is an important, maybe the most important result in category theory, which is that any mathematical object is summarized by those arrows that take that object as a codomain. So if we gather together all the morphisms, let's make the drawing. If we have a mathematical object here, we don't know anything about it, but if we know all the arrows that go to this object, if we have the entire set of these, then we know everything there is to know about this object.
I love
That's
that the most important result in category theory is a lemma.
Yeah.
It's not the fundamental theorem of algebra or something like this. It's a lemma.
I was just going over it today. I have the proof right here.
Oh, amazing!
Did you guys see Emily Reel's presentation?
Yeah.
Yeah.
It was.
You
really
asked
good.
the question, Dennis, right?
Yeah, I asked the question. It was like a really basic question. That as soon as I asked it, I was like, "Oh, that's makes like it makes no sense for me to ask that question," but it was nice anyway. Yeah, but the lemma thing also is it's kind of I feel like it's kind of a way to intimidate new people to category theory, because you think to yourself, well, if this is a lemma, then what are the theorems in this?
I mean, I think it's called a lemma because it's pretty quick to prove. The proof is like a few lines. The proof is a few lines long. Usually, like a lemma, a theorem takes quite a bit of work, because when you're actually in like the abstract machinery of it, it like comes pretty quick. But it's pretty profound though. So
yeah, it's not measured by how profound it is. It's just measured. The lemma is just measured by like how many steps it takes.
Yeah, I guess so.
In a way.
Yeah.
Yeah, but if we have time, it'd be nice to actually derive it. I think it would clarify a lot of category theory. But for now, let's just take this sentence as on face value. And then. So composition is actually a double thing, right? We can build morphisms from other morphisms by doing this operation. And this is a picture of that, right? Just like in this example here, where did I put it? Right, we built a new morphism by kind of chaining together these other ones here. You can depict that more concisely with this kind of diagram. And just as we can build new morphisms, we can also decompose them into their parts. And I think that's actually more interesting than building new ones. Because when we decompose them, we figure out what they're made of, and we can then extract information from that morphism. So that this is a theme that can't really get into that much, but actually I have some examples of it later on, but just keep that in mind that it's connected to this idea that we have equivalence classes of morphisms. We want to be able to subdivide them into the morphisms we care about, which satisfy some conditions. So this is a way of saying, given all of the maps between X and Z, and given all the morphisms between X and Z, we only care about the ones that go through Y or factor through Y in some sense. Right, so this is a constraint because not necessarily every morphism from X to Z can be decomposed along with Y. Right, so this is another type of constraint. Okay, so let's talk about constraints in general. So like from the set theoretical world, we can think about a very simple type of constraint as a relation. And this is familiar grounds for us because Badiou covers this, right? So I just quickly, these 4 things saying that reflexivity means that an element of a set is always related to itself. That's the property of reflexivity. Symmetry means that if A is related to B, then B is related to A. Antisymmetry is if A is related to B and B is related to A, then A must be equal to B. Meaning I can't have a double relation between 2 different elements, right? In some sense, antisymmetry means every symmetric relation reduces down to the reflexive case. Becomes A equals A. Transitivity means if A is related to B, B is related to C, then we can do a kind of a thing here, right? We can eliminate B and just relate A directly to C. And then we have the 3 different types, right? Preorders. So the first 2 properties, partial orders, which is the first 3 properties, equivalence, which are the first 2, and then skipping antisymmetry and then getting transitivity. Okay, so all of this can be formulated in terms of morphisms again. So from the morphism perspective, a relation is just another function, and actually there should be a domain here, but it takes some domain to the product of 2 sets. In other words, it selects pairs of elements, X and Y, where little x belongs to big X and little y belongs to big Y. And then, okay, again, the same caveat applies. We want to be able to think about this in terms of extrinsic behavior of the morphisms and not in terms of the points. We want a point-free definition, a point-free viewpoint, let's say. Okay, and then also I thought this was an interesting to add, interesting thing to consider, because sometimes you might have a relation, sometimes you might have a morphism that is not quite a relation or doesn't quite fit a relation, right? Because these properties, they're pretty stringent, they're pretty strict. If you were to take one of these elements out, you wouldn't have that relation anymore. But you could say it's still a morphism. So here I can, just to make clear what we're saying here, so like if A and B are 2, C here, right? If A is related to B, that's kind of like saying we can draw a little circle here, right? This relation R, let's use a red. And already you can kind of see how morphisms kind of work here, because when I draw a circle around these things, that's the same as saying like this, right? and B.
Could you not think of the relation as an arrow from A to B?
Like an internal relation, like this to this.
Yeah, I'm just thinking
Yeah.
because these relations are pointed, right? Like the order matters. Like for example, if the relation is a partial order,
Yeah.
then it's not just like a
Yeah.
set. There's an order to it.
Yeah, I think.
I mean,
oh, okay.
when it's an equivalence relation, it divides your like domain into classes,
actually,
right?
You're right. You're right. Actually, that's what the product. This is not truly a product category, right? Products are this. They're actually made up of does that make sense? Like every object in this is actually a pair of elements.
Okay, you're mapping from A to the product of A by A, right?
Yeah.
So the red on the left is what?
It's the domain of the relation. So yeah, I see the problem though. So let's try to fix that. Yeah, because I forgot what was the domain here. I think X by Y. So we want a subset of X by Y. Oh, that's true, right? It's
the same thing.
It's a
but
subset of X by Y.
Yeah, but in this case,
Well, it depends what kind of relation, right?
Yeah, I think all relations.
Oh,
have
and then
this,
like
right?
in the ways they overlap depends on the other. Because if it's an equivalence relation, then it's just they're completely disjoint, right? In the product.
Yeah, that's right. The codomain is X by Y.
Yeah.
Your question, Dennis, was that if X by Y is codomain, so what is the domain for R? Is that the question you're asking?
Yeah.
Yeah,
the
but
domain
isn't
for
it
R.
just the case that you have like say a set A, and you're mapping the relation is like mapping A and B to the product of A with A, which is a subset which has A and B inside.
So where is B coming from?
It's also in A.
Oh, so set X and set some other. So sorry. So it's a. So it is. Relation is so domain is set X and the codomain is X by X. X cross X. Yeah, or A cross A.
Yeah, really, the domain doesn't have to be anything in particular. I mean, the domain is just the related, let's say, the number of related things. Just, they could be points. It doesn't matter what they are.
Mm-hmm.
Right? What matters is that it's first that it's injective, and second that it only selects the targets such that the property holds. So let's say if I were to pick A and B, and then I also were to pick out this A and C, if I'm saying this is a equivalence relation, then I also need to choose C, B, and C, right?
Mm-hmm.
So what's contained here? Let's write it out, right? A R B, B R A, A R C, C R A, right? These four relations are holding here, right? In other words, I'm saying that my codomain, the image of my morphism, it hits these points. It hits A comma B, B comma
So
A.
yeah, the domain is going to be the relations themselves, the distinct relations, right?
Yeah, the domain is just
makes sense.
they're points of relations. Yeah. what is it, C comma A, right? And then, yeah, the domain in that sense, they can just be these points, we call them, right? And they're injective. So each one of these is hit. Yeah. And then, okay, so my point here was to say, like, this is not an equivalence relation yet, because C and B should be, by transitivity, C and B need to also be here, right? So B, C, and CB, they're not included in this map. Therefore, this red map is not quite an equivalence relation. So morphisms in that sense are generalizations of relations. They don't have to obey this, right? So they're not quite a relation, but then we can talk about morphisms that get closer to that relation, right? So we can actually order morphisms such that they're ranked according to how close they get to being an equivalence relation, let's say. So this one is more of an equivalence relation than, let's say, this thing, right? This is another map. It's also a valid map from here to here, but it doesn't quite capture as much of the relation as the red map. And then finally, the map that's the best in some sense to capture an equivalence relation, that would be something that has all of these, right? So like it has 6 points and it hits everything. Okay, so just because this is going to become more important later, this idea of not quite a relation and then gradually becoming more, let's say, incarnating the relation better and better, right? Okay, so another mathematical object is a poset. Posets are sets with a partial order relation. So again, reflexive, transitive, antisymmetric. If we put that relation on the elements of a set, we get a poset. And then this yields a new type of function, right? So we're still within the category of sets. So we're talking about functions rather than morphisms in general. But a function which goes between posets and preserves the order is called monotonic, right? So an example of this would be, in this case, the relation we're talking about is this, right? So A is less than B, B is less than C, A is less than C, right? This type of stuff. This is, so that, in other words, that looks like this, right? But since it's a partial order relation, we can have something else like this, right? Right, so let's add in A is less than D and D is less than C. But notice that B and D are not related at all, right? That's the partial thing. And we talked about this a lot for Badu. So we call a monotonic map something that preserves the order here. So monotonic would be like mapping B and D to some element E, right? And then A would get mapped to F, and C would get mapped to H, such that the order is maintained.
But both B and D were mapped to E.
Yes, both B and D were mapped to E. So this is order preserving, but it's not injective.
Yeah, it's a never decreasing function.
Right. Yes, that's actually the meaning of the term monotonic. Means I never map something on the left to something that's less than what it should be, right? So like I can never get the situation where B gets mapped to H and C gets mapped to E. Like,
Yeah.
can't cross like this, right?
But
Because
this turned the partial into a total order, no?
exactly, that's another thing. In this case,
But
this
it's a case, or it's necessity?
it's just a case. That's just just happens to be the simple example I showed. But like we can make it.
The monotonic function there transformed one collection which is partially ordered into one that is totally ordered. That's what we're talking about, right?
Yeah, but is it necessary that it's totally
No.
ordered, or just
No.
Okay, yeah.
Just because it's mapping B and D to the same point, right? To the point E, so you have a totally ordered set in the other side, right?
Yeah.
Yeah, no, it doesn't have to be. But if you want to think about
Okay.
like the graph of it, right? Like in like a simple like one-dimensional scenario, it's just gonna be a function that never decreases.
I
It's just
see.
always going up or constant.
Mhm.
But here, like it can still have branchings, yeah.
Okay.
Yeah. So yeah, in this
It's
case,
completely
let's say
The definition.
E gets mapped to I.
Yeah, you can be monotonic and not injecting. So that's what you're saying.
Mhm.
Okay.
Yeah. So here we kind of collapse one branch, right?
Yeah.
The path AEC was collapsed into, sorry, ABC and ADC were collapsed into just FGH.
FGH, right.
But E gets its own representative element here, right? So yeah, monotonic just means the order was protected, right?
That's an interesting thing. I was asking myself, what does that has, if that has anything to do with the logical notion of monotonicity or non-monotonicity, which means if you have a non-monotonic inference, it is one that is not constant under further premises. If you add certain further premises, the inference does not stay the same. I'm not sure how to map this idea to this kind of machinery right there.
Mm-hmm.
Because it's quite an important notion in some of the stuff I study, like Robert Random, inferentialism, this kind of thing.
Mm-hmm.
That inferences are non-monotonic. So everybody that says, oh, you know, this kind of philosophy presupposes a really great stability and everything, and a transparency and semantic transparency to everything and all that. This is just false because they don't understand that this is non-monotonic, right?
Mm-hmm.
So I was just wondering how to map this logical idea of monotonicity and non-monotonicity to this categorical theory representation of this. I'm not sure if
I mean, I would say it's exactly the same, right? Because if something's non-monotonic, it means it doesn't recede. So if you think of it in the context of like a Hating algebra, which is like a model of a logic, right? If you have a non-monotonic function, that means it can like recede in truth. So I guess it would probably be the same thing, yeah.
Okay.
Yeah, it all depends on, and this is like true for any category theory thing. The first thing is to define what the arrows are, right? So like in your case, if you're talking about inferences, right? So inferential ranking, right? If
you have A, you have B. If you have B, you have C. Something like that.
Yeah. So like A, B, C, D, right? So then that if A is true, then right, then B, C, D, right? Yeah, exactly. So then the question is, monotonicity here would mean maintaining this chain, but not necessarily like we can collapse this, right?
Okay. Yeah. It's clear.
So
That's
yeah,
clear.
exactly.
That's great. So the idea is that non-monotonicity in logic is the idea that if you add further premises or further collateral inferences, you may modify the mappings. So this is the idea. So it makes sense.
I think another way of saying this is to say that you might have preserved the basic enchainment, but if you look with more richness to the inferential tree, you would see, for example, that it's true that if A then D, and if D, then Q, but perhaps from C you don't get to Q, right? So if you collapse B, C, and D, that doesn't mean that you always get Q.
Yeah.
Yeah, this is interesting though. Yeah, I was thinking a very non-mathematical example would be like take all the tasks you need to do in a day. You can apply a pre-order on them depending on how important you think the task is, right? Like pay my bills, right? Yeah. Eat food, and so on. Like these are not necessarily related in an order relation. They might be the same, but they both are more important than, let's say, like watch TV, right? Right. So in that sense, watch TV is less than both of these, and and so on, right? And then these are more maybe read Badu, right? So in that sense, when we order our day, which is our time is a total order, right? We have to collapse this somehow, like into, so like let's say, okay, given a monotonic function here would mean like, let's do it in order of importance. So watch TV first, then do this, like, right? We have to make a choice here, but we're allowed here to make either choice. I could eat food first, then pay my bills, or I can pay my bills and eat food. It doesn't matter because they're not related, but they both have to happen before I can read Badu, right?
Yeah, because you're mapping something that has more than one branch just to align, basically, right? One branch, you have to make choices.
Yeah, but the monotonicity is preserved.
Yeah, as Yasha said, it preserves the increase. It still is an increasing function of importance, let's say, or conditioning. So that was preserved, right?
Yeah, because paying my bills and eat food is not in the original tree. They are not ordered by importance, so you can just you have a choice then that does not defeat the monotonicity. Yeah, I see.
Yeah, in this case, this is still injective also, right? Because here we gave the example of a non-injective monotonic because B and D mapped to G, so we collapsed B and D. But in this case here, we did not collapse anything. We made a choice and we ordered what was previously unordered in a way.
You could collapse, for instance, watch TV and eat food, for instance.
Yeah, actually, yes.
And it's pretty common.
Yeah, exactly. Yeah, we could have done this as well. Yeah, and this is an example of composition, right?
But that would not be a monotonic mapping if you collapse eat food and watch TV, because it does not preserve the original order.
I think that the good examples of monotone maps are in that 7 sketches of compositionality, where they do. I'm not sure how to. This page here. I'm not sure if I can share it. This one. Just 1 second.
Yeah, that's a good one.
What's that text? 7 sketches. What's that?
It's a really cool book called 7 Sketches on Compositionality. It's like a primer on category theory. It's an invitation to applied category theory.
Nice.
Yeah, I highly recommend. Yeah, after this, if you're still interested.
Yeah, of course, I will look into it.
Yeah. Anyway.
Yeah, I think you're right, Reza. Yeah, the collapsing thing, if it doesn't respect the order, yeah, it's not really monotonic anymore. In this case, watch TV is less important than eating food. Therefore, we can't collapse them.
Well, if it's a strict less than, then yeah. But if it's less than or equal to,
oh, you're right. Yeah,
it might be okay.
Actually,
yeah.
You're right. Yeah, because of if it's less than or equal to,
Things can stay the same.
Mm-hmm. Yeah, I wonder if the anti-symmetry condition means that we cannot have.
You need to share your
so
screen
anti-symmetry
again,
would let you have that. Yeah, exactly.
Okay. Okay, so now that we understand monotonic, now we can understand adjunctions, right? Where in this, it's a very specialized sense, right? The more general notion of adjunction will appear later in category theory. But this is one of the very clear, at least to me, examples of it. In some sense, you can think of adjunctions as being not quite a inversion of a function. So given a function from C to D, we can define a reverse function, R, that goes back from D to C, such that this condition holds if it's a right adjunction. And in the case that it's a left adjunction, then this condition holds. So how do we make sense of this? Okay, it has everything to do with the thing I was just showing you about collapsing things and making choices between things. We can make certain choices that preserve the ordering relation in two different ways. So it's not quite a monotonic inverse. So maybe the best way to show that is by showing what a monotonic inverse is first, right? So a monotonic inverse would be if f of x, sorry, go back one. If x is less than or equal to y, then f negative 1, sorry, f, look at this, right? So this is a monotonic function. And then if it's a monotonic inverse, then f negative 1, f of x less than 2. Right, this must also hold. Okay, so this would be like saying we go from x, so let's say p to, so p1 to p2 by f, and it's monotonic, right? Then we go back here, and we also preserve the thing so that we get back to where we started, right? It's isomorphic. So an adjunction is one that you don't get back to where you started, but you still maintain some amount of order relation. So if I go F and then I go back through R, right? So R follow F, right? It's not the same as F negative 1 follow F, right? They're not the same, but some order is maintained. And similarly, a left would be like this, right? Is not the same as, right? Yet some order is maintained. Okay. So what condition is it? In this case, it's this, right? So if f of x is less than y, then x must be less than r of y. So let's write that down here.
Yeah, but in the two definitions you gave there, you wrote them the same way. Are the arrows going the same direction in both cases?
Yeah, that was my question as well.
Yeah, L and R are both
From P2 to P1.
yes.
But
Yeah, maybe I should define that first. Right? Here. So R is P2 to P1. L is also P2 to P1. And F is P1 to P2.
Yeah, but you see that in the red and yellow definitions you gave there on the right side, you wrote exactly the same thing.
What do you mean? R follow F and L follow F are different.
Yeah, it's just a negative condition, right? It's not the same.
Okay, this is not a definition, it's just a negative condition. Both of them
Oh,
are
yeah.
just, okay.
Both are different from F minus 1.
Okay.
Yeah. Exactly. Yeah, I mean, that's a bit confusing because it doesn't give us any information about what this is. It's just saying it's not the inverse. I'm just saying it's not like we're not getting back to where we started. However, even though we're not getting back to where we started, we do have a bit of information here. So this theme that we kind of saw earlier was like a morphism that is not quite fitting a condition, right? It doesn't quite fit the condition, but it fits some other weaker condition. This weaker condition is still interesting. And in category theory, it's like really important later on because it kind of generalizes a lot of ideas in logic and kind of produces new information from a given morphism. So given some F, we can define the right and left junctions according to this, right?
I understand. Okay, I understand it.
Yeah.
So it's actually that the order is preserved, but it's the order between something in P and a function of P2 into P1. Yeah. Okay.
Yeah. Yes. So this is taking place inside of. Did I write this correctly? Yeah. F of X is taking place in D, and Y is also taking place in D, whereas X is taking place in C, and R of Y is also taking place in C. Okay.
I see. Okay.
So yeah, maybe we'll call it.
Yeah, can you write that here so we have one screen so we don't have to go back and forth?
Yeah, good idea. F of X. Right, so right, left. Okay, so let's try to draw this out. Okay, so we have some order relation here, right? It does something like this, right? Let's call this X. So let's do it here. This is P1. This is P2, and let's define another order relation here. Okay, so so let's say X is
P1.
Yeah, X and Y are actually in
P1.
P1, right? No, but then this F of X, we're saying F takes here to here, right? Meaning F of X must be in P2.
Yeah, Y is in P2, X is in P1.
Yeah. Again,
Yes,
in the
exactly.
7 sketches, there's a good example already drawn on page 19, the bottom.
Oh, then maybe that's better than to use. Let's see.
Page 19 of the PDF or the text?
Yeah, if you just write to go page 19, it's 29, but it's actually 19 in the. It's under Galois connections. For some reason, Galois, between drinking and being like the first emo guy, he was also already aware.
Sorry, what page of the text you said?
Yeah, the one that Dennis has here.
Hmm.
It's page 27, but in the PDF it's 29.
Yeah. So yeah, this actually is way clearer than what I was drawing. So yeah, given P and Q, it's way simpler. I thought for some reason I needed 2 separate structures, but if you just have a total order, 1, 2, 3, 1, 2, 3, on each one, you can already see the adjunction taking place. The adjunction is such that we are allowed to map, although it doesn't tell you exactly how these adjunctions arise from a function, but yeah, given some monotonic map, we can define these 2 adjunctions to be the way of mapping such that you respect the order, but you have some ability to make a choice here, right? Because a direct inverse here would be mapping 1 to 1, 2 to 2, 3 to 3. That's invertible in the normal sense. Notice how this F here, which is the blue lines, it's not an invertible function.
Mm-hmm.
Right? Because 1 and 2 are collapsed to 1. However, if you were to follow this arrow, so 1 to 2 to 1, and then back to P again, you would still maintain order.
You do?
Mm-hmm. Because 1 to 2 maps to 1, and then 1, whether it maps to 1 or 2 again, it's going to be less than this.
Less or equal to, yeah.
Less or equal to 3.
Yeah, because this is less than equal, okay.
Yeah.
But if, for example, 1 from Q were to go to 3, then it's not an adjunction.
Yeah.
Yeah,
Well, yeah,
it basically like pushes everything up further from where it came from, right?
Mm-hmm.
So for everything in the codomain, for it to be a red adjunction, where the ascent has to be greater than everything that has an arrow to it in the domain. Right?
Mm-hmm. Yeah. So yeah, let's try to summarize it this way. Whenever I have a choice between 2 things I can map to, I want to choose the lower of the 2. Right. So for the number 2, I have 2 choices of where I can map and still be a monotonic map. Right. 2 cannot map to 3. We know that because that breaks monotonicity. But 2 can map to 2 or 2 can map to 1, and that will preserve monotonicity because 1 is less than 3, right? And 2 is less than 3. So I have 2 choices here. The left adjunction is saying that I always choose the lesser in this case of posets. The right adjunction means if I have 2 choices, again,
Go to the higher.
I choose the higher, yeah. 1 can map to 1 or 1 can map to 2 because I can collapse 1 and 2 into 2 and still maintain order. So I want to choose the higher of the 2. So in that sense, we are splitting the notion of monotonicity into 2 distinct ideas. And this is a powerful tool and a very interesting tool that I don't fully understand, but it's core to category theory, which is that for any concept or for certain specific concepts, we can find these adjunctions that split that concept into 2 kind of dual or opposing versions. So you can think of monotonicity as the total concept, of preserving order. It's maps that preserve order in general. But the left and right adjunction of a monotonic map, they give you the two principled ways of doing that are not isomorphic, right? The most general case would be an isomorphic map. So 1 maps to 1, 2 maps to 2, and 3 maps to 3. That's already given by the notion of monotonicity.
And you're saying this generalization of monotonicity is important later on in category theory.
Yes, it's not necessarily monotonicity. This monotonicity is one concept that has adjunctions, but there are other concepts that can have adjunctions as well.
But it's interesting because intuitively adjunctions seem to separate a certain structure even further from the things being related, right? Because you're actually recognizing some information about the ordering in the relation between the two, right? Between, as you said, f of x and y, not x and y, right? So it might be the case that it didn't preserve it totally in P1 and P2 as you define it, right? P and Q here, but it's kind of in between the two, right?
Yes. It's in between the two. It's two extremes of satisfying the same condition. A really interesting case of this is actually I don't know if we can find it in NLab maybe, but a junction where it pertains to this. I'm looking for specifically that thing about how the for all operator and the there exists operator are adjuncts to each other. Maybe if I look up. As a junction, yeah, love your quantifiers. Yeah, so you know in logic you have the for all something, for all of f, or sorry, f is some property for all elements in A. All those elements must satisfy some condition, right? And the there exists of A means there exists at least one that satisfies that property. Well, these two are basically a right and left adjoints. They're splitting in the same sense that we, although it's probably hard to see it, in the same sense that we split the notion of monotonicity into two here. We can split some function into the for all of that function and the there exists of that function.
Whereas if it is monotonicity, it would be both either for all or there exist.
Both either for all or there exists.
Yeah. So for the left and right adjunction, you can have one is for all, the other could be there exist, or one could be there exist, the other one for all. But
no, it's always one of these is always the right and one is always the left.
It has to do with the thing you talked about it mapping, it choosing always the lesser or choosing always the maximal for that section of the order, right?
But
Yeah.
could there be?
Let's say if it chooses to use a Badiouian language, if it chooses the enveloping, it will go for all.
Okay.
If it chooses the minimal value,
There
it will go
exists.
for the exist.
Okay.
Yeah, perfect. And we kind of see this more.
But doesn't matter which one is which. Like you could have in that example of P and Q, could there be that the left adjunct go to the highest, the higher one, and the right adjunct to go to the lower one?
No. In this case, no. One of them. So there's a reason why one is the left and one is the right.
Because it's less than equal to?
Yeah, because of the less than equal to, left is always going to be the lower.
The lower one, okay.
Right. The least that satisfies. So that
So
actually explains existence and right for
depends
all.
on the relation. If it was greater than or equal to, then the order would have been reversed.
Yes. Yes, that's a good way to think of it. Yeah.
Mm-hmm.
Yeah.
Yeah, so the right adjoint always goes up, sort of, right? The left adjoint will go down.
Yeah, but this up and down is relative to the relation we're trying to.
Exactly,
so because we're looking at less than or equal to, that's why left is minimal in this sense. But we could just as well flip all these arrows. So instead of one is less than 2 is less than 3, we have 1 is not greater than, but some other relation to 2, other relation to 3, right? So 1 is related to 2 and 2 is related to 3, another way, right?
So if a function is both a left and a right adjoint, is it always an inverse?
Yes.
Or something close to an inverse?
Yes.
Okay.
Yeah, because and I was trying to show this with this example, but I wasn't able to. But the idea that this case, right? This is like the general case of inverses, right? This preserved, because I took, in a trivial sense, the inverse takes every element of the domain back to itself, right? Inverse composed with some function. So for any x in P1 and any y in P1, I'm going to get back x and y when I go to F and then come back. So it satisfies this condition. This condition is the condition that is split into 2 in this case. So you can think of these two as like 2 halves of this more complete condition.
Mm-hmm.
So this is what I mean by saying like taking a concept and dividing it.
Yeah, but in that general case, is x and y are within the same domain? Because how could f apply to both x and y?
Yeah, this is the confusing part too. X and y in this bottom one are different.
In where are you pointing?
Oh, here, x and y are in different domains.
Yeah, x belongs to P1, y belongs to P2. In your general case, it seems that they are in the same, like they are both in P1.
Yeah.
Mm-hmm. Yeah.
Yeah, because
he's just being inconsistent with his notation, is all.
Yeah,
The
I think
x and y up above are both from the domain of F.
Mm-hmm. Yeah, I don't have a very precise way of formulating this yet. I think we should look at the 7 sketches maybe. But in general, I want to say that you're able to combine these 2 statements again.
Actually, I think if you get the order of -1, then you can correct that so that x belongs to P1, y belongs to P2. Because f of y should not make sense. It should be f minus 1 of y.
Yes. So you're saying, okay. Let's try this. If x is in P1, then this must be true, right?
That is right. That is right.
Exactly. Yeah. Oh, sorry. So if X is less, this is the right way to write it.
This is the right way to write it. Yeah.
Let me delete this.
Wait.
Yeah, this
no.
is confusing
No?
for me. Because
No, because here, wait, X and
Hmm.
Y would be in different domains, right? Because F
Yeah.
inverse, the domain is the codomain of F.
Yeah, but aren't we? Isn't
No, Y is in P2.
no? Why is okay? But in your whole first example, X and
I
Y
think
were a partial order in P1, and we were mapping that partial order in a monotonic way to some stuff in P2, right? And at first the question was, okay, when we go back from P2 back to P1, what has been preserved? And we were talking about very strong preservation, where we get, if we had X smaller or equal to Y, and we had f of X smaller or equal to f of Y, when we went back, we got back X and Y. And we saw that there are weaker conditions, which is we get back something which doesn't necessarily get us X and Y again, but still preserves some of the relations because let's say X remains smaller than f of Y.
Mm-hmm.
So I cannot tell from this inverse, from this returning mapping, that X is smaller than Y. It doesn't give me both in preserving their order, but it does give me that f of Y is smaller, is larger than, is greater than X.
So finish the sentence, Dennis. So f of X less than f of Y.
Oh, this is wrong. Let me. I'll move this out of the way. This is the inverse example. So is this. This is monotonicity in general. The key is to formulate it in terms of inverses, right? Because we want to say that the inverse is a perfect case of something, and the right and left adjunctions are the imperfect case.
Mm-hmm.
The not quite inverse, right?
Yeah.
Okay, so this is the perfect case.
Yeah.
In one direction. Then this is the, so perfect, sorry, this is monotonic.
It's monotonic, yeah.
Now this is the perfect case of monotonic inverse. Inverse, right? Which is to say, X less than or equal Y implies that F negative 1 follow F, meaning we made a round trip.
Yeah.
And we found out in that round trip, we're still this, right? This is the perfect case. Now we're splitting this into two, which says that it, now the F of, maybe I just copied the formula wrong. Let's double check here. Yeah, F of P is less than Q if and only if, yeah. I see the problem. X and Y here is actually should be formulated in terms of different, because P and Q here actually belong to the different domain and codomain, right? So it's F of P less than or equal to Q implies that P is less than or equal to G of Q. Yeah. So this is a slightly different way of formulating it, because it's saying that we have an adjunction, a connection between the left and the right adjunction. So this is the.
So isn't like in your perfect scenario, aren't you replacing F and F minus 1 with left and right, L and R? So
yeah,
in this case,
exactly.
Instead of Fx less than Fy, you say Lx less than Ly, right? And then in terms of F minus 1, you say if the inverse, you say X less than Y says that R follow L of X less than R follow L of Y, right? This is what we want to say.
Yeah, so this is different. This is not the same thing as what I was talking about. I'm talking about a specific case where given an F, we can formulate two inverses, two not quite inverses, one called the R, one called the L. In this case, the case that they talk about in Seven Sketches, which is a Galois connection, which has some relation to what I'm saying, but it's not exactly the same. The F and G are like this. Right,
yeah.
So F takes P to Q, yeah.
I believe the left and right adjoints always come in pairs, right? So if you have something as the right adjoint of something else, then the original thing you started with is the left adjoint of the right adjoint.
Yeah, that was my understanding too. So the
Yeah,
diagram,
but then you can
have,
get chains of them.
Yeah.
So for here, you actually have two pairs of adjoint maps, right? You have F and R and F and L. So for F and L, F is a right adjoint, and for F and R, F is a left adjoint.
Yeah, so is it true that L and R have the same domain and codomain, or are they flipped?
Yes. Yeah, they have the same domain and codomain.
Okay, because the example in Seven Sketches here, they have different, right? Because F.
No, but they do because these because okay, so it's because you're doing it in ref. Actually, oh. No. So a left and right adjoint will always have different codomains and domains.
Yeah.
Just the ones you're writing here, like go back to your original picture. L and R are not left or right adjoints of one another, right? So this is why you have to think of it in pairs. F and R, so the adjoint pairs are always going to be flipped.
Right.
If L and R were the same, if L equals R, then it's an inverse. So it's a weird like half sort of inverse.
Yeah, is it like this? Like, so it's,
yes.
Yeah, I was confusing it because I thought R and L have some relation. It's actually F and R.
In general, I don't think they have any relation.
Right. Yeah, that makes more sense. So when we talk about
and like chains of adjoints are an important thing that I don't quite understand, but they come up a lot.
Yeah, that's important. Yeah, I mean, I'm totally unprepared to go into detail on this. I was just trying to depict like the general notion of splitting this notion, like whatever the notion is in this case monotonic, we're splitting it into these two component pieces, right? But yeah, you're right. That's where the confusion is.
But isn't this connected with the fact that the monotonic inverse preserves all meets and all joints, right? It returns you back to the partial order as you had it, right? The left and right adjoints show that you can actually preserve one without preserving the other.
Yeah, that's
right. So if you have a return that keeps all the joints but doesn't keep all the meets, you get the left one, right?
Yeah. We haven't gotten to the joins and meets yet, but yes, that's the better way to approach this, right?
Yeah, I'm just trying to say that, I mean, this is profound because it takes something that's supposed to be a primitive, which is either you preserve or you don't preserve order, right? And it divides it into two, into this, as you said, that very nicely, like a half relation sort of thing, because you can actually go back and keep some of that information, but an information that usually we conceive as being like unified, like either you have both and you reconstruct it, or you don't have any. So if you can actually reconstruct from the standpoint of the meets or from the standpoint of the joints, right? You get, I think that's how you define the, I'm not sure if that's correct, but that's how I understood you defining the left and the right, this choosing the lesser or choosing the higher.
Yeah, that's, this is actually a more productive way of thinking of it, I think. So imagine you have a pre-order here. Choosing the lower means we can collapse these points only if they are lower. So let's say these three here, we can collapse them into a single one and still maintain order, right? So this, all of these mapped here, right?
So they will be, for example, they're all less than, so this mapping makes it, obtains for that little definition you gave, because all of this new lower point here, it will be less than f of, right? This f of whatever we want to call it, it will respect some of the ordering, right? I don't know how you write this, like this little x here, it will be less than all of this anyway.
Yeah, exactly.
So in relation to this, you see that something was preserved, right?
Yeah,
so,
and then the right adjoint would collapse it upward. So you take the higher of the two approaches.
So, I mean, from what I get just from the cursory discussion is that something that was supposed to be just thought of this sort of primitive idea of inversion, right? You can actually split it into something that preserves some information, but not this perfect inversion, right? So we still keep some idea of the ordering, but adjunctions show that you can actually explore, as you were saying before, some sort of structure that is not so clearly reducible or equivalent to the original order that you have.
Yeah, it's defining two extreme points of some new conceptual space, let's say. In this case, the space of monotonic functions, right? The space of monotonic functions is a lot of functions, right? All possible functions that preserve order. And the left and right adjoints are two poles of this space, two extreme points. In this case, it looks kind of trivial because it's only 3 points. But if you imagine like a huge space, right? There's many, many, just as we said earlier, there's n to the, or b to the a, an exponential number of morphisms.
There's a really crazy example on the next page of the sketch book. The example 1.7, I think it's just above that page. Before the back to partitions part. Yeah, just above that. Oh, your version doesn't have it.
Yeah, I might have a preprint of the.
Perhaps they removed it because they begin by saying this might not be very rigorous, and then they make a crazy example with animal populations, but
Yeah.
anyway.
Yeah, I haven't gotten. I think this is actually a work in progress, or it was when I downloaded it.
I think your version is more final than the one that I have.
Oh, they took that out. Okay.
Yeah, I think they took it.
It's too crazy.
So is this, maybe this is obvious, or maybe this is the point that we are going toward, but like as an example, we just saw functors that map in logical world, functors that perform the function of transcendental indexing just in reverse, right? So like basically map a region of an object to a territory. And then basically maps the envelope of that region of the object, which is an atom, to the envelope of that territory. So is this a monotonic function, or is it a left and right adjoint?
It's a monotonic.
It's monotonic.
Yeah.
The reason that I'm
preserves
saying, right, but there has to be an additional condition for the functor, and that is the compatibility of the elements. Whereas the codomain of the functor does not have this compatibility requirement. Like compatibility, the concept of compatibility of elements does not exist for transcendentals. That's what I'm trying to say. So anyway, so it sounds like monotonic, but I was just not sure.
Yeah, I do think that this is important for us to discuss what it means to explore transcendental. I mean, but you never mentions the joints or things like this, but just from the fact that we have a specific formal language to talk about information preserving morphisms that turn, let's say, this vast partial order into something that is, let's say, simpler, less rich, but still with information inside of it that pertain to that partial ordering, right? Which was the monotonic function. It did preserve something like that continuous crescent function, but it doesn't necessarily preserve all the incomparable elements in a preorder, in a poset, right?
Yeah, I mean, this is why it wouldn't be that difficult for us to come up with a junctions for Badu, because since we were working with posets, right, in a partial order relation, adjunctions are exactly what Gabriel said earlier about morphisms that preserve either the top or the bottom element, right? So if a morphism preserves only the top elements, then it is I want to say the right adjoint.
Yeah, that's right.
Yeah.
And then the left adjoint preserves all the lower elements, right?
Yeah.
So in that exact same sense, we can collapse. We can do two types of collapsing.
I think this might be useful. I mean, I don't want to open the gates of hell, but this could be perhaps exemplified with our restaurant example, of different ways of keeping. Carol is already going like, oh my God, but like different ways of preserving some information about the world of spices. But okay, I'm not gonna. Okay.
Carol, remind us of your funny joke. What did you say? What's the transcendental of the pig? What was it that you said?
What? The transcendental of what? I don't remember.
Pork, transcendental of the pork.
Yeah, the envelope of the pork and the fish.
Yeah, what's the envelope of pork and fish? Yeah, something like that.
Yeah, that's our final project, actually. So
okay.
Badu is only a stepping stone to the theory of
The first gourmet theory of worlds.
Okay. Would you care to elaborate how does this fits into the restaurant metaphor?
No, my point is just that you can conceive of a poorer transcendental. So, in our very basic, in our very basic study of what it means to have a measuring of a world's transcendental, we realize that we need a further step from worlds to transcendentals to something that we call, let's say, some metric. And that seemed to be something that moves from partial to total order, or from the infinity of the transcendental to something that is more simple, right? So it is about losing information and preserving information. So in that case, it seems like these things might be relevant, but
definitely,
from a compression of information that, the information gets more relevant because it's compressed in a sense. For example, there is a good discussion in the sketchbook on what they call level shifting, which is the possibility, for example, of keeping, for example, the right adjoint. I think that's not how they discuss it, but this idea that you can have a mapping or a morphism that will still tell you something about how things are coming together, but it's no longer having information about the things that are coming together. That's a very simple way of talking about moving from a scale of analysis to another, because you know how things are hanging together in a certain sense. You just don't know what these things are anymore. You don't have enough richness to describe them, right?
Yeah, I think in the context of the Badiou's project, you could think of the left and right adjoints. If you're doing it of like an object, for example, it could be like a scaling up or a scaling down, right?
Yeah.
So the right adjoint like scales up. It can bring you to like a more general context, and the left adjoint would bring you to a more specific context. So that would be like a different choices in the transcendental functors, right? They could either bring you up or bring you down.
Yeah, that's what I thought.
Yeah, I think that's a good way to think about it.
Yeah, there's definitely very ripe for research, because no one's ever done that with Badiou. So I think
in our example of the world of food, it would be the difference of talking about the spicy dish or about the pepper in the dish. Like, you go to the components of the dish, and you get a view of the let's say the common points inside, or you get the view of what envelopes all of them, right? So spicy, you see my point? Like the spicy dish is like from the envelope standpoint. Mm-hmm. The dish that has peppers is from the conjunction.
So in this case, the spice is a transcendental, and pepper is the element.
Yeah,
spicy
pepper
dish
is common.
Yeah, pepper is the conjunction of, like, things are in conjunction with peppers, rice, peppers, and so on. And the envelope is that it's a spicy dish, right?
Yeah, what do all spicy dishes have in common? Pepper. And then if you combine all spicy dishes together, if you envelope them, you get spiciness in general.
But spicy itself is a transcendental, is a degree. It's not an atom.
Yeah.
No, you don't have an atom. Right?
It's not an atom. We would need another dish that embodies spicy.
Right. So in this case, the functor would be a particular kind of pepper, like pepper X, which is the envelope of. Why are you laughing? We're talking about. This is an important.
This is metaphysics.
Yeah. This is metaphysics. So.
Perfect, man. I have an analytic background, so I know. Discussion metaphysics.
Well, that's the beauty of Badiou, that it gives you the machinery that you can talk about dishes in a very, very precise way.
Yeah, of course. Not discussing this. I agree.
Oh, I love it. I'm laughing out of happiness.
Anyway, that's interesting. Okay.
Yeah, definitely. We need to contribute to the world this theory, because the world needs it right now, I think. So for quotients, we have, again, this idea of constraining morphisms, right? So previously we talked about monotonicity as a constraint, right? Let's parse down the number of morphisms from two sets to only the ones that preserve order. That's monotonicity. Quotients also do something like that. They are a special type of morphism, except they have to follow the three properties of an equivalence relation, right? So that's reflexivity, symmetry, and transitivity. And what that looks like, it can be summarized in these circles here. Basically, it's a partitioning of your space into disjoint subsets, right? No overlap. That's important. So in this case, I painted them with different shades of some green color, which I will explain in a second. But yeah, it's important to know that between any of these two shades, if you were to take the intersection, you would get the empty. But if you were to take the union of all these rings, let's say, or these circles, these sections, you would get back the original space X.
They are
So
not circles. They are not concentric circles because you have to have an empty intersection. They are different rings and a circle in the middle. This is what you're saying.
Yeah, exactly. Then this is a limitation of this drawing. It looks like one is contained in the other, but I'm saying they're not, right? I'm saying each little ring is its own subdivision. In the diagram, so how do we draw this picture in a category theoretic way? We would say of all the morphisms between the white X, right, the white circle, to some gradient space, color gradient space, we only care about the maps which factor through this thing here. So I'm pointing, I don't know if you can see my mouse, but I'm pointing at this bottom left drawing.
Yeah, we can see your mouse.
Okay. So this bottom left drawing, it's a way of conditioning or adding a property onto this diagonal arrow, right? We're filtering it only for the ones that factor through here, and to factor through here just means we've taken some arbitrary property, some relation, and we've related the points on this space according to that. In this case, we could say the relation has to do with the distance from any point to the center of the circle, right? So I say, let's say the circle is radius is pretty big. It's the size of the Earth. Then I say, well, everything within 100 miles of some arbitrary center belongs together. They're all related. So we draw a circle starting from the center, right? Centered on the middle of the world. And everything in there is related. And then I say, okay, if you are between 100 miles and 200 miles away from the center, then you are also related, right? And these are, in math or whatever, that's called equivalence classes, right? So in other words, I'm grouping everything together as if they were one. That's what this little formula here stands for, that 1 comma n as a subset of the natural numbers, right?
Yeah,
n can be arbitrarily.
Called the quotient map, right? So it's a map to the equivalence classes.
Exactly.
Yeah.
It's a map. So first we considered equivalence classes or equivalence relations in general, and now we're showing that equivalence relations can be thought of as morphisms from one space to some smaller space. Right? It's smaller because there might be an infinite number of points in X, and there's only a finite number of buckets or bins that these points fall under. And now again, we can take this one step further and say, okay, well, we can collect all the possible relations, and we can start to order them together, right? All possible relations of a certain type. In this case, I want to take all relations that subdivide my space according to the radius, distance from the center. So, right, because I chose some arbitrary n here. I said there's 4, right? And if you see this middle picture, there's the dark green, some lighter and lighter, and finally the white, right? So there's 4 bins here. Well, I can choose 5 bins or 6 bins, right? I can choose arbitrarily number of bins. And the limit of that process is a pure gradient from the middle to the outside. So it's a way of, like, imagine I have a knob in a machine and I twist the knob and I make these regions arbitrarily fine, arbitrarily precise, right? And I'm tuning my relation, right? So this a morphism in that sense can be tuned to an arbitrary degree. And that's all I wanted to depict here, is that relations themselves can be related, relations of relations, and we can order them just like we order other things. Okay. So now we're switching to lattices. We already kind of covered this.
The question, did you answer that question?
Yeah, quotients are always epimorphisms.
Mm-hmm. And why is that?
Because, so recall that an epimorphism is one that basically hits all of the elements of the codomain, right? Leaves no elements out. So if you think about our codomain as the number of buckets, a equivalence relation says that basically says that all elements belong to some bucket. Therefore, all points in this white X need to fall into one of these 4 buckets. Therefore, all 4 buckets will get something, right?
So that morphism between the white and the binned circles is an epimorphism.
Yes.
Okay.
Exactly. Yeah. And this is actually a specific case of a more general phenomenon called epi. So what is it called? Epi-iso factorization. Right. Given any map, we can factorize it with an epic or epimorphism, and then an injective or iso, not iso, but let me go back here. Got the word already.
Mono.
Mono, yes.
Yeah,
Epimono factorization. So an epimono factorization is to say that given any morphism, we can factor it into one epi and one mono, so that the mono follows the epi.
Right. Remind me, mono was which one?
Mono is injective. Mono means every point
injective.
Gets one unique.
I see. Mono is injective, epi is surjective.
Yeah.
Okay.
In sets.
In sets. Right.
In sets specifically.
I remember that from the sets.
Mm-hmm.
Okay.
Yeah. Yeah, and this is also something that we should think about. Like, why is it that any morphism can be factored in this specific way? Well, why is it that the first arrow must be epi and the second arrow must be mono? That's a nice category theory question, I think. Okay, so then lattices. Okay, we already covered this.
Just another question about logics of words.
Yeah.
So again, transcendental indexing and the functor are both epimorphism. Because you got to be able to find a degree for every possible element of the multiple that appears.
Exactly.
And then for every degree of the transcendental, you should also find an object or atom. So they are epimorphism between the two.
Yeah, so objects, so we can say, for example, that existence is a surjection. Because like you said, everything has a degree of existence, right? So degrees of existence are like the bins.
Right.
The bin space. That's true. And then the transcendental functor, however, the one that maps back from our transcendental back onto the set is not surjective, it is injective.
Injective, I see.
Yeah.
Yeah, certainly, but you does not discuss this, but I have a sense that you could argue that the transcendental functor is also surjective.
Yeah, what if we did this, actually? This is what Badiou shows us, right? That the map from A to A can be decomposed. There's a certain map from A to A, which is decomposable into an identity map to the transcendental, and then from the transcendental back to A using FA. So that this is right? Something like that. Yeah, it's not exactly this because identity is a two-arity function, but we can instead of identity we can use existence, which is one arity, right?
Especially because the transcendental functor takes degrees of existence, right?
Yeah.
So FA takes degrees. So you have like, I don't know, in the classical world, just 2 degrees. FA takes these 2 degrees and maps them into A.
And also in a within an atom, it's enough to know levels of existence, right? Because then you can just get the degrees of difference by just taking the conjunctions between the two.
Yeah.
Atoms. So that's another thing we haven't covered. But yeah, the idea of fixing one of the elements in this identity function, right? So A of X is equal to identity like that, right? Is that what you mean?
Oh no, I was just talking about that within an atom you have the equality of, if 2 things are compatible, right? That the conjunction of their existences is the same as their level of identity, right? If I'm thinking correctly.
Correct.
Oh, right,
Yeah.
right.
Yeah.
Yeah, that's this, what, like this one?
No, the half integral.
That's localization.
localization.
That's look. It's like the little star thing. It's what it means when they're
Yeah.
compatible. Yeah.
You're right.
Yeah. And compatibility is like sort of like they're within an atom, right?
Yeah. So compatibility is a
just
relation. It's an equivalence relation, right? Because it's symmetric. If A is compatible with B, then B must be compatible with A.
Yeah.
It's transitive and it's reflexive. Yeah. So. Yeah, exactly. So yeah, I mean, it'd be good to also. I didn't have time to do that here, but yeah, we should think about how we can take this quotienting and apply that to compatibility and existence and those things. Yeah, and then lattices obviously are very relevant for understanding the transcendental and the structure that it induces on an object. But I think we already kind of covered this. The only thing is like we can define a semi-lattice, which has only meets or joins, but not both unique meets or joins. And also, I don't know if we already covered this, but this is an example of what's not a lattice, right? This is not allowed because it's not unique. These two bottom elements have two different joins. Okay. So yeah, that's not a nice structure for Badiou's project. Okay, also to get from lattices to eventually to hiding algebras, we have to pass through this distributive law, which states that we can do this thing. And again, in Badiou's terms, this V, this OR, should be replaced by the envelope. And this AND would be replaced by a conjunction, right? And he states somewhere in the book that this holds, right? And that's because a hiding algebra is a distributive lattice. Also, one thing we've been talking about is the concept of a locale as kind of a generalized space. The difference between a frame and a locale is important here. Distributive lattices, like the one that satisfies this condition, is actually called a frame. Right? The locale is specifically when we flip the order of the frame. So that they're equivalent notions, but kind of opposite in some sense, right? And this also, I think, has some relevance in the contravariance of the functor. Why is it that the orders are flipped in?
So frame points down, if I'm right, yeah, and the locale sort of points up in the sense that like locale is kind of like inclusions, like a topological space.
Yeah, I wasn't able to find a clear thing on that. I saw somewhere that the frame is as the frame of opens.
This is something that I've been struggling with figuring out.
Frame of opens, it's just a store that sells frames that it's open.
Yeah.
Yeah. So you have this definition, which didn't really help, but
I think it has to do with the because a locale is a generalization of a topological space, which is a set of sets that have arbitrary meets and finite joins.
Right.
So locale might be sort of the other way around, you know?
Yeah, so you think frames point down and locales point up?
I was thinking the other way around, but it's probably not important.
Yeah, I think that's, they're equivalent, basically, in terms of the amount of information that they contain, I think.
Yeah, there are some technical differences, but I can never really figure them out.
Yeah, that's something we should consider later on.
From what I understood is that the frame is let's say more of the topological picture, right? As you said, it's more, let's say it's organizing the information in terms of something that is like inclusion, whereas the locale is more of a logical point of view. Is that it? Because it's organized in terms of order.
I was thinking the opposite, but maybe you guys are right.
But in your definition, what do you mean the order is reversed? Because the lattice that has distributivity is defined by a particular kind of order relationship among points. So you are saying it is reversed. You mean the order relationship is reversed, or what is reversed?
Yeah, the order relationship is reversed. The thing that's missing from the definition to make that relevant is one of these cares more about the arbitrary joins, and one of them cares about arbitrary meets. So recall that I don't know if I skipped through that.
Okay.
A complete lattice is a lattice where every subset of a P has a unique join and meet. Whereas a semi-lattice only has meets or joins. Okay, so if I tell you that my lattice is guaranteed to have a unique join for any subset, then I believe that's a
Locale.
Right? Yeah, because locales are like topological spaces, and in topological spaces, you can have an infinite number of unions and still be another set, a set in the topology. So let's actually add, yeah, this is a perfect segue here. If you look at this, this is a definition of a topology, which corresponds to a locale, I think. If Yasha, that's what you were saying, right?
Yeah.
This is a closed under unions, infinite number of unions, and finite number of intersections. So I think the difference between locale and frame can be just thought of as, instead of infinite unions and finite intersections, we have infinite intersections and finite unions.
That's the frame.
Yeah, that's the frame. Infinite unions is a locale. Infinite intersections is a frame.
Yeah, okay, I see. So the differences in morphisms, it's in, I'm seeing it in Wikipedia, actually. I literally have a thing that says the differences. Nice. So it says the morphisms in a frame are functions that preserve finite meets and arbitrary joins.
Okay, so actually frame then.
Frame is more like a topological space.
So
and locale
right.
is the opposite. So it usually, so it's gonna be the opposite. It's gonna preserve in arbitrary joins and finite meets. Yeah.
So which
Finite,
one is a topological space, locale or frame?
A frame. Yeah.
Frame.
It is a frame then.
Yeah.
So the one that has arbitrary number of meets is a topological space.
Yes.
Okay.
Yeah, the example that actually Yasha gave me here, a great example, is if you have the number line, right? The real numbers, right? What is the standard topology here? It's the topology of open ball definitions, right? So like this is like a an open region, right? And then so is this one, and then so is this one, and so is this one, right? If you were to map all this, you would get something like this kind of structure, right? So this would be nothing, empty, right? And then you have like these infinite many of these things, right? And then they're unions, and so on. Okay, so obviously, if I take the union of any two of these segments, I'm going to get a new segment in this space. So in that sense, it's closed under unions, infinitely many, right? Because it's the real number line, it's infinite. But if I were to take the intersection and I were to take it infinitely, so the intersection of all of these would be the empty set again. Like what does all these regions have in common? They have the empty set in common. But the problem is the empty set is not an open region. Right? So this is where the caveat comes into play, that the infinite intersections is not itself open, so it cannot belong to it. Is that true actually? Because a topology must have a minimum element, right?
You can have so yeah, but the thing is, in the topology as a lattice, it's only the open sets. So if the intersection of a bunch of things is a closed set, then their intersection in the lattice is going to be the empty set. Because the topology is sort of like doesn't see the closed sets, right? But like here, really the example you want to think about is if you have like a infinitely many nested sets around that one point.
I see.
Right, you can think about like each one is 1 over n away, so they get infinitely closer.
Right.
The important part is that they go infinitely to the point in the middle, right? Then if you intersect them all, you're left only with that single point.
Right. So that would be like of all the opens.
Yeah.
Or take I. Yeah, something like that. Okay.
Yeah, so that shows you how you can get infinite infinite meets that are not preserved.
Right. They don't qualify as.
Yeah.
So the key here is that there's a closure. We want the closure condition to respect one or the other. And I wonder if there's actually an adjunction there, just as we were talking about preserving one but not the other half of a thing. I wonder if frames and
I think they're more.
Yeah, there is exactly. I see this right here. It says the definition of Heyting algebras crucially involves the existence of right adjoints to the binary meet operation, meaning that to go from frames, if you have a frame, if you want to go to a locale, which will preserve, you need a right adjoint to the binary meet, meaning that you need to preserve arbitrary meets, right?
Right, so we're saying...
As well, because a frame normally does not.
Yeah.
But then the locale does.
So we're saying there's some kind of adjunction here?
Yeah.
No. Okay. Okay, but this is getting off into the weeds of the technical sides. But yeah, this picture kind of depicts this closeness, right? You can, for any two elements, if you can union them, they should be in here. And also the difference between frames and locales seems to disappear if we're dealing only with finite subsets anyway, right? The distinction between arbitrary joins and finite joins, or vice versa, doesn't matter if we're dealing with a finite space like this.
Right? Wait a minute, I'm confused here. So are we saying topological spaces are the ones that have arbitrary joins or arbitrary meets?
Arbitrary meets. So
okay.
So it's unions.
So
meets are actually intersections, I think.
Oh, sorry, joins.
Yes. Yeah.
Oh, wait.
Right.
Joins. Yeah, my bad.
Joins. Okay. So in that case, then this diagram is topological spaces are lattices that have arbitrary joins.
Yeah.
Yes.
Okay.
And finite meets.
And finite meets. So in this case, topological spaces are locales.
Yeah, either the other frame. We have to figure out for sure.
Yeah,
anyway.
I'm not sure. Yeah, I mean, this
it's not super important for the specific thing we're talking about.
Yeah, it's not very important. They can be formulated as both, though. Okay. Topology is a huge field that
this is fascinating stuff, guys.
Yes,
this is
it
like
really is.
Tour de force.
I think also something that is important. Yeah,
magnificent work.
Thank you.
I think something that is also crucial there is that in this discussion of frames and locales, and it's at stake, let's say, the conditions for, the pointless topology and this sort of logical space without
elements.
Without elements, yes. Right. So, we're one step before the whole stone duality issue, right? Because under certain conditions, these spatial frames are equivalent to spatial locales, right?
Yes. Yeah, this is the the path from topology through logic to topos. And it's a path that requires the stone duality to be generalized to, because stone duality originally has to do with Boolean algebras, right? We have to take that and generalize it to Heyting algebras. So
now, if this is a pointless logic, then how do you define order? What is the order among?
Yeah, well, I mean, these spaces can be thought of in terms of their behavior under intersection and unions, independent of the points, right?
Yeah.
So these are like open sets. Each of these colored things.
Yeah.
These are open sets.
It's thinking of the ordering of open sets as primitive, instead of starting with points and deciding what your open sets are from there.
Mm-hmm.
It's going the other way around.
So it's like a lattice of open sets.
Mm-hmm.
Yeah, exactly.
Yeah.
Exactly. Yeah, so lattices are nice because they allow us to make this very clear jump from topology to logic and algebra, right? And so, yeah, that's the space in which we're trying to work with to understand Badiou, right? Because he jumps between the two.
Right. So in this case, can we say just loosely that consistent multiplicities are open sets in this case?
Yeah, I think
so.
Yeah, my impression from what we discussed this far is that what Logics of Worlds is doing is using this specific equivalence between this lattice of open sets and logical spaces to come up with a analysis of logic that is not constrained by, let's say, that very classical principle that we found in being an event where, well, you can only analyze multiples in terms of these closed sets, right? So
okay, so put it another way. Objects then are open sets in this case.
Yeah, I think so. Yeah. I mean,
yeah, that's a better way to think about it.
Yeah, I think so. I mean, the point is that to be objectified in a world doesn't mean to be made more solid in the sense of, so I identified the exact, closed subset of stuff that is this object. It's on the contrary, is, let's say, you are working in a space where everything can be made of open sets without this pointed definition, right?
Right, and you can basically, in the world of appearing, you can have arbitrary open sets like in any topological space.
Yeah.
Yeah. So I think this is really the profound thing, right? That from sets and power sets to post sets to topology to this pointless topology, you're moving to a discussion that, though it's grounded on the multiple, it opened up for it to be sliced in, let's say, a much richer way without losing the logical expressivity, right? And a way of talking about the logical constraints of that space, right?
It's also better just to think about, I think open sets are sort of like the building blocks of spaces in a more general sense. Mm-hmm. Spaces can be made of points too, but points don't really have to make this sort of like continual, ever-flowing, intersecting space that we sort of have our like intuition of appearing in,
Fascinating.
I'm muted. Yeah. Okay, so let's...
Dennis, you will share this presentation or no?
Yeah, I can share this.
Only to himself.
Yeah, no, I'll definitely send it. I think, it's an incomplete presentation because it's...
Well, we have the recorded thing, but I wanted to have the opportunity to go through this again.
Mm-hmm. definitely. Yeah, I just need to export this. Right now it's just an HTML file. I think I can export it as a PDF. This slide is actually a kind of an aside, but because it's delving into topology a little more. But I just wanted to point out very basic concepts like continuity and distance. They are built on top of the notion of topology. So given a topological space, we can define a continuous function as those that kind of take opens to opens, right? So
actually, it's the other way around.
Is the other way around?
Remember right? It's the inverse images of open sets are open.
Right. The inverse of open is, so if the codomain is open, if you hit something in the codomain and that happens to be open, then your domain must be open also.
Yeah. So it means that things that are close together should get mapped to close together things.
Mm-hmm. Yeah. And this kind of makes sense with the definition of open set, which we didn't go into that much detail, but we can think of it as a set that allows you to zoom in arbitrarily, right? So like normally, if you have like some discrete points here, that's it, right? There's nothing more. But imagine if I chose a point right on the border here. If it's an open set, then actually, if I were to look closer here, I don't know if I can do that. This thing. Well, it's actually easier if I were to actually look into this point, I would see that it is actually not at the border. And in fact, there is no border, right? I don't know if that makes any sense. Like, so it's a set without boundary. Another way to say it is that for any point, no matter how close you are to what you think is the edge, you can always draw a little boundary around it. And this circle, which can be a sphere or whatever, will be inside of the space. Yeah. So, and that is why you can do this operation of zooming into a continuous function, continuity, and which is to be, I think Yasha can talk more about it, but that you can distinguish that from like smoothness. The function that you zoom into might not necessarily be smooth once you've zoomed into it.
Mm-hmm.
Right? Yeah. So this has to do with derivatives. So smooth means the derivative is continuous, or that you can take its derivative differentiable everywhere, right?
Right.
So you don't have any like sharp peaks, but then there's like levels of smoothness. So you'll see sometimes if you look at like any kind of analysis stuff, you'll see like C to the N, right? So C0, it's all the set of functions that are continuous, and C1 is all them that are smooth, meaning the first derivative is continuous, and then C2 is second derivative is continuous. So then like it's like a nested set, right? Because there's a lot of continuous functions, and then for it to be C1, it has to be C0.
What function is when the second derivative is smooth? Like acceleration is smooth?
Yeah. Generally, when you have your first derivative being smooth, the second one and the rest will be as well. But it's difficult to get examples that aren't.
So
that's
like
right.
the first derivative is for velocities. If velocity is smooth, then acceleration is equal to 0. Or acceleration is constant. That means that
no, if it's smooth, it can still change. It just means it doesn't change sharply, right?
Oh, I see. It's
There's
not
also
monotonous.
front,
Okay, it's not monotonous. It's smooth. Okay.
Yeah.
Yeah, there's an ordering on the functions in that sense. Where we can maybe say that there's an equivalence relation or equivalence classes of functions, which are ranked according to how smooth they are. The highest being the infinitely smooth, right? No matter how far you zoom in, you're always going to get a smooth function. That's this crazy thing, right? It's very well-behaved function. But then you have like
you can take infinite derivatives.
Infinite derivatives, yeah, and you always get something that looks like you can do calculus still, right? Yeah, so that is a secondary thing from the definition of open spaces, right? Open sets. So from open sets, you can get continuous functions, and also you can get a metric space. These three conditions actually look very familiar to the conditions on the identity function. I've kind of mentioned this before, but I don't know exactly how to map them. But it's basically saying two things can have zero distance only if they're the same point, right? If this D is a distance function, it's something that measures any 2 points on some space and tells you a number in R, let's say the real numbers, but it can be something else also. It gives me a distance of those 2 points. So if there's no distance, they're the same point. And also this distance is symmetric. If I'm 5 miles away from you, you're 5 miles away from me. And then it obeys the triangle equality, which makes sense because like visually even at most this, let's say C, right? C cannot be bigger than A plus B, right? That's
yeah,
what this is saying.
the main difference between this and the identity function is that this has to be mapped into the real numbers.
Yeah. Right.
And
real numbers,
things always
yeah.
have to be comparable, right?
Mm-hmm.
So it always has to be on like this sliding scale. So you can have like a similar idea of metric that is not in this, but it wouldn't exactly map over.
You're right, yeah.
Because it's about generalizing the idea of distance between points, right?
Yeah, exactly, yeah. I think identity is more general than distance, and that's,
Yeah.
I mean, that's interesting. That means that, you know, like we've been talking about, we can derive different notions of distance from identity.
Yes.
By some operation that collapses some stuff, right?
Yeah.
Just like we did that with this crazy stuff with I don't know where we did that, but yeah, this collapsing procedure, taking a partial order to a total order. We can define some kind of distance or metric space. So the identity function kind of gives you like a space with a bunch of other metric spaces inside of it. And then, of course, this is also related to the measure theory stuff, which I didn't have a chance to prepare for this presentation. But it's also, I think there's some relation between measurability and metrics, but I'm not really sure what that is.
Yeah, measurability is defined on sets. Metrics are defined on individual points. So that's the difference.
Okay.
But I think you need a metric for a measure.
Right.
Actually, maybe not. No, you don't. You just need a sigma algebra, which is basically defined on like open sets, essentially.
Yeah.
So it's similar.
Yeah, that's important. Yeah, this idea we keep going back to of like, how do we turn this into like a ruler for different types of concepts, right? The whole Hegel discussion we had, and also like passing from quality to quantity and so on. It fits into this discussion. Okay, and then quotient spaces. So we already talked about what a quotient is, and now we know what a space is, so we can combine those two concepts to come up with a quotient space, and that is the result of taking one space and identifying certain points on it, which amounts to kind of gluing those points together or thinking of them as the same. So in these pictures, the purple and the pink and the green, green should be glued to green in an oriented way. So if a point is here, maybe draw it, right? You want to imagine it. A point here should be considered the same as a point here. And a point here should be considered as the same as a point here. and same here should be considered the same as here. All right. Another way
I think a good way of thinking about this is if you like Lacan's reason to use it, right? Because if you take this square like here, as you were doing it, imagine that you have like, this is what's most other, and this is what's most inner. And for him, what he plots is like what's most other to you, outside of you, is identical to what's most other inside of you. And what's most identifiable outside of you is identical to what's most identifiable inside of you. So that's why he comes up with the torus as a, let's say, the shape of the psychic space. Because stuff that you identify as being most other to you, it's the same, it's equivalent to it being something in you that you don't recognize. Whereas something that is most inside of you and seems like the stronger thing about you is identified to the thing outside of you that you recognize as being most identical to itself as well. So this is glued to this.
So the idea is if you glue them together, then you get the shape of a torus.
Yeah, because if you glue this, yeah, exactly.
Yeah, so that takes some like thinking for a second. But if you imagine, let's glue this green with the green first, right? What do we get? We get a cylinder, right? And then what happens to these in the cylinder? What are these pink things? They're circles. Now we glue the two circles together. Yeah, actually, in this picture on the right, it should be
inverse. Yeah, but
the inverse. Yeah, you glue the pink stuff together first, and then the green circles are glued together. And then you can see that I kept the pink and the green here to show you what happens to those lines. And then in the case of a sphere, we can do the same thing, right? Or a circle. If we take if it's a finite circle, a circle with a border, or I think Yasha, you pointed this out, if this is all the points at infinity, right?
Yeah, also back to the torus, a good way to think about it is as R2 mod Z2. This is how
You're muted, yeah.
Did you say mod Z2?
Yeah, I think so, but he got muted somewhere.
Hello, can you hear me now?
Yeah.
Okay, sorry, my microphone was tweaking out. Yeah, you can think of it as R2 mod Z2. So R2 is like the plane. Mod Z2, an equivalence relation on it, such that for a pair of points, X, Y, if you can add a pair of integers, so if you can add a pair of integers A, B, so X plus A, comma, Y plus B, then they're identified. So they're the same. So that's an equivalent way of putting this. This is just like when you look at just like the 0, 1 square, you know?
Yeah. Another way you can think of it is if I'm a guy, if I'm a person that exists on this space, let's see, this is my field of view. Like I can go this direction, this direction. If I go here, I'm going to come out over here. Right? Similarly, if I walk up here, I'm going to get back to here.
Like the old
Star Trek episode.
Yeah, Star Trek, or like Pac-Man or whatever.
Yeah, Pac-Man.
Yeah, but that doesn't allow you to distinguish between spheres and toruses yet.
It does. What do you mean?
Well, because if I go back to that image, in a sphere, if I go this way all the way, I'll come back here. And if I go here all the way, I'll come back here. Because it's the same thing as doing this or this, right? You're still crossing at 2 points. Like, if you did this, but you didn't cross your previous path on 2 points, then you are on a torus, right?
Yeah.
See my point?
Yeah. So this is where you get to more like topological properties of a space. So like the difference between the sphere and the torus here, like yeah, in both cases you can walk in orthogonal lines such that you get back to the same place. But one thing you can do on the sphere, not in the torus, is you can take what I guess Dennis will get to this, but you can take the loops, right? So if you imagine that path around, you could take continually shorter and shorter paths until eventually the path just ends up being like a teeny tiny little loop till it gets contracted to a point. And you can continuously do this, right?
Yeah.
You can't do that on the torus. There is, if you want to go around sort of like one way around the donut, there is a minimum length that will have to go to get all the way around.
Yeah, like this will not contract to a point.
Yeah.
Because of the hole in the middle.
Yeah.
Yeah.
Yeah, I was thinking about the distinction based on Jordan curves, and like no two Jordan curves that intersect in a sphere will not intersect at 2 points, whereas there are Jordan curves in a torus, like this, the one that goes through the alma here, and this one that intersect only at 1 point.
Yeah.
So this defines the difference in genus of the two spaces, right?
Yeah, that's one way to see it. Yeah.
Yeah, this gets into the whole thing with homology and homotopy. I think Jordan curves would be related more to homology, and this
continuous deformations. Yeah,
the deformation thing is homotopy. So yeah, I actually took that out of the slides because I didn't want to distract, because I wasn't sure if that was relevant to Badu so much. But yeah, I really like this picture of, so like imagine you have some really complicated space. It is actually related to Badu in a way, because it has to do with how do we get information out of space, right? So we don't know anything about this space, so what do? Let's take a space we do understand really well, such as S1, which is the circle. This is a horrible circle, but let's imagine it's a circle, and let's project that circle onto this space a bunch of times. And in fact, to make it easier, to make it make more sense here, let us choose one point on this space to be a privileged point called the base point, and let's map this circle up infinitely many times on starting and ending on this point. So what that will look like is something like this, right? This is one map. This is another map. And then let's make a third one, right? This is another map. And there's infinitely many of these, right? Circles. And then let's make a rule that says if we can turn one of these circles into the other circle through continuous deformation, meaning no cutting allowed. Like I can't cut this circle up into just two lines, but it has to maintain a loop. And if I arbitrarily adjust it, if I can turn one circle into another, then I count them as the same. So this is an equivalence class. Then I count how many equivalence classes there are on this space, and that tells me what the space is. So exactly, as you guys were saying with the sphere, right? Donut. I can project this circle many times. So I can get a bunch of these. Let's say the privilege point is here. I can make a circle here. I can make a circle here, make a circle here. All these circles are the same. Yeah. That's fine. That's one. But if I make the circle here, I can't continuously transform this circle back into these other ones. It'll get stuck. This circle is an obstacle to that. So, and the trick with this is to not think about this hole as an actual hole in some embedded in some space, but rather it's kind of an abstract obstacle to the contraction process. to the deformation, right? For some reason, we don't know what it is. Doesn't need to be even like thought of in a spatial way necessarily. It's just for some reason this morphism cannot be turned into the other morphisms. Yeah, that's the homotopy or the fundamental group.
Yeah, and that's what that defines that these two arrows that we had before are actually different from these two, right? Because the fact that not everything can be contracted in this way. There is something, let's say there is an equivalent class of circles here that is disjunct from this equivalent class, right? See my point? No.
Sorry, I didn't hear what you said. Could you say it again?
No, yeah, my point is just that this is a more precise way to talk about the fact that these two things here give us a sort of, they allow for continuous deformation, like for example, if we had a sphere where all the infinite points are identified. So all of this will be contractible to one.
Yes.
But the fact that we have this other thing here, which is disjunct from that previous one, right? It's not like in the sphere. This is equivalent to saying that there is a different group of concentric or continuous deformations that will not map to that first point, right?
Yes.
So almost like these things here identify a point of deformation that is these things here that is different from these things here.
Yeah, I think I see what you mean. Like, I'm not sure how we can derive from simply looking at the identification on the left. Maybe
because this is equivalent.
True,
this is an equivalence, right? Sorry, like this.
Yeah, I see.
And this is an equivalence relation, right? And this is another one. So in the way that you were describing, this equivalence concerns if things are contractible to a point. If there's two, that means that there will be at least two ways of doing this in that space.
Well, the two sort of gives it two, I guess like degrees of freedom. Right? The homotopy group actually ends up being Z2. So the integers time the cross product of the integers with itself. So you can go a certain number of ways around one hole and a certain number of ways around another hole. But this like restriction on the fundamental group, which like actually grows it, comes from the equivalence relation.
I see. Okay.
It doesn't have to do exactly with the like sides of it.
Yeah. No, I'm just trying to like move from equivalence to the sort of visual idea of the whole to just what it, I mean, the sort of invariance that it actually implies on the space, right?
Yeah.
Okay.
So just tie this back to what we discussed. Each of on the torus, on the shape on the left hand side, the one that basically gets transformed into torus. So just to tie it back to the terminology, torus is the quotient space.
Yes.
And then we apply a morphism to exactly what in order to get a quotient space? To a lattice?
No, we're applying it, well, yeah, in a sense, a topological space is a set of points plus a lattice that is closed under.
So then in this case, the shape on the left is a topological space, and the shape on the right is a topological space, and the morphism is the glue, that the gluing that we do to the left in order to get the right. Okay.
Exactly.
They're pictures of the same thing. The ones on the right are like embedded pictures. The ones on the left just show you the equivalence relation.
Oh yeah, that's a good point.
The whole space is already there. Like they're equivalent pictures in a way.
Yeah, they're equivalent, but I think we could say that the plane is not equivalent to the
Yeah.
The plane itself is not equivalent to the torus. It's only when you apply the quotient to the plane, to the Euclidean plane, that you get the torus, right? Or
Right.
in other words, R2.
Yeah, that's right.
Like exactly
But,
what Yasha was saying, R2 mod Z2. That's the
but there is when
algebraic
we go
way.
to the third one, the Klein bottle, there is no Euclidean space that can be turned into a Klein bottle.
Oh, it can. This is still the Euclidean space. It's just identified differently.
Yeah, locally it can still be Euclidean, right?
You can, you just lose the concept of orientability, meaning that locally that you can mirror yourself and you can't tell the difference. Because imagine if you're a point and you have some notion of left and right, and if you move over that line that's going down and you come out the other side, then everything's flipped. Or I guess if you have a notion of up and down, actually.
I see.
It flips it. So it's non-orientable. So it's sort of.
Okay, so coming back to the question. So I like that the left and right are the shape of the same thing. So in this case, the arrows on the left side is basically the application of the quotients to the Euclidean space.
Yes, exactly. Exactly
Right.
like we
So-
identified that circle with the color gradient
Right.
by using the bins, right? First we applied the bins, and then we applied the color.
Correct. So in this case, the Euclidean space is without those arrows, and then applying those arrows means we are basically applying the quotient morphisms to the Euclidean space.
Exactly.
Right.
The quotient morphism is determined by the equivalence relation.
We lost you for a second, Jacob.
Oh, the quotient morphism is determined by the equivalence relation.
Right. Okay.
Yeah, that was the thing I was trying to show, that every equivalence relation determines a morphism, or it can be translated into a morphism.
Now the difference between torus and the sphere is that on the sphere we have one equivalence relationship, whereas in torus we have two equivalence relationships.
Two classes.
Two
In the torus,
classes.
we have two classes of loops. Classes meaning two count as ones, let's say.
Sorry, say it again.
We have two things counted as one, right? Like, that's not the right way. We have infinite number of circles, but we create two bins for them.
Right. And we get the hole in the middle of the donut because we have two quotient morphisms.
Yes, exactly. Z2, in the case here, let's see.
It's not exactly
Back
two
to-
quotient morphisms, but it's more that the equivalence classes are two-dimensional.
So we have two equivalent classes in the case of torus, whereas for a sphere, we have only one equivalent class.
Well, no, not exactly, because for the torus, technically, you have infinitely many equivalence classes. Really, the equivalence classes are each of the points of the torus.
I see.
The same way the sphere.
What do you account? How do you say that in like a description that you have two colors, two arrows, two colors, two bins in Dennis's parlance, whereas for circle you have only one arrow? How do you describe that?
Yeah, so the
One color, I mean.
equivalence relation on the circle only has to do with the boundary of the circle. So it's only on the boundary, and the rest of it doesn't have anything on it at all. So it just glues the boundary to itself. So it's a weird example because it also like would deform the geometry of it. So it's actually not like, spheres are not really great because you can't really give a good quotient of them from Euclidean space. It doesn't like compactify everything into an infinite point, because that's what that really is, right? It's collapsing a one-dimensional thing to a zero-dimensional thing, which is the point.
Yeah, I don't know if I have a slide on. Oh, okay, this next one will show us this kind of in a clearer way. I don't know if you guys are okay on the time, because
I still have
we're only
an hour.
okay. So
I am okay till top of the hour.
Yeah.
Okay. So I think we can cover at least a few more slides then. I think we're almost done with the topology part. We're going to move on to the category theory soon. But just to talk about why is Z, what is the point of like Z2, mod Z2 or whatever? It actually has to do with the fact that a circle can wind on itself infinitely many times, countably infinitely many times, right? Sorry, what was that?
In both directions too.
In both directions, yeah. So actually one circle is counted Z because of how many times it winds on itself. I think that's one way of thinking of it.
Algebraic.
And you have Z because it can go both sides?
No,
plus and minus?
No, I think that actually has to do with the orientation, the question of orientation of your space. So when you define, I didn't put it in this drawing here, but when it's oriented one way, then only certain maps that maintain that orientation will satisfy that condition. So it's actually two different spaces, let's say, right? One space is oriented clockwise and the other space is oriented counterclockwise. But here I'm not talking about that difference. Yeah, do you guys see this picture here, or the spiral?
Yeah.
You see that? Okay. So let's talk about covers, because this kind of condenses the conversation we were just having. So we know that spaces can be different, and we know that using maps or morphisms, we can get information about a space, right? But let's also talk about the case where two spaces actually look the same from the perspective of another space, right? And this captures the tension between local and global, which is going to be really important in the notion of topos and of sheaves, right? So this commutative diagram says that given a circle like the one on the left here, this spiraling circle, and a morphism which takes this circle, this spiraling circle to the pink circle here, it will commute locally with this picture on the right. So this thing on the right is let's say 4 disjoint circles. They don't loop on themselves. It's not a single spiral, right? It's 4 separate circles. But from the perspective of a point on the pink circle, we can draw a gray box here, which is like the perspective of this pink circle. And from that perspective, you cannot tell the difference. Okay, that's what this commutative diagram tells us, right? We're saying that the maps that go from the top left to the bottom right here, or the bottom here, those maps look exactly like if you were to take this and take a green circle and multiply it n times.
So they are like left cancelable?
Left cancelable. No, in this case, they are not left cancelable because multiple point, left cancelable means injective. And injective means one point can have at most, one point on the codomain has at most one point in the domain. In this case, we're mapping all 4. We're collapsing these 4 points on the green into a single point on the purple. So it's not injective, but it is surjective.
It's surjective.
Mm-hmm.
Because right canceled.
It's right canceled. So this is the notion of a cover, right? A cover is basically expressing the fact that we can find a set which contains another set, which the collection of subsets contain the set. So let's step back and consider sets and not topological spaces. So if we have a subset Y of X, then if we choose a certain other set of subsets of X, and if all those contain Y, then we have a cover. Let's draw this. So let's say in this case, this is X, and then this is Y. So a cover of Y in this case would be something like this. Let's say one more thing would be this. So this orange, so what is the orange thing? Let's call it X1, X2, and X3. This is a family of subsets, right, of X. If I take the union of these things, right, so if I take the union of Xi, then I can say that Y belongs to this. So then this thing is a cover.
This is actually important because a territory is an example of a cover.
Yeah. Intuitively, I think you can think of it as like it satisfies a condition, but it can do a little more than satisfy the condition in a way. Because in this case, if you union X1, X2, X3, you actually get the entire space. Right? But let's, even just to clarify more, let's say there's some points out here that are not even considered. So yeah, this cover, when you union them, you get something that contains Y. But it does a little more than containing Y. So earlier when we talked about this not quite a relation morphism, you know, a morphism that almost fits a certain relation, but not quite. This is kind of like that from the other direction, because it's a morphism that covers a little too much, right? You can see here that this is a little more information than is needed to satisfy Y.
It doesn't have to cover too much, but it can.
Yeah, exactly. And that's the point. Yeah, it doesn't have to cover too much. So, given a cover, we can define a refinement V of a cover, which is basically shrinking. This is what this condition says. We're basically shrinking our cover. So V is a restriction of U. Right, and it's formulated in this kind of confusing VI, which is just they can be disjoint. It's like a family of subsets, right? Yeah. So like, let's use green this time. So let's say U. This cover is called U. Okay, U. We can come up with another cover like this.
And call it V.
And call that V. So we say V refines U. I should not have chosen V and U because they look so similar, but yeah, V refines U. Why? Because they're both covers, but V is contained in U. If you were to take the union of all of the parts of U and you make this total U, which is another set, right? All this orange stuff, and then you were to take the union of all the V, the union of all the V is contained within the union of U. And that's what this condition describes. And actually, I wasn't precise enough here. It means that in the refinement for each individual family, it must be contained. So this green thing is contained in this orange thing. This green thing is contained in this other orange thing.
It's like a least upper bound with regards to U. So it's actually ordered, right?
Yeah, it's the greatest lower bound.
The greatest lower bound, yeah.
Yeah.
I mean, it goes back to
In
your
some
20
sense.
questions game, if we want to discuss what it means for like a logical approach, right?
Yes, exactly. If we think of, if we move away from the spatial metaphor and start thinking about it in terms of constraints on actually what Caron was saying, like inferences or constraints on a sort of specification of some kind. Y, the subset Y is like a entity in the world or some kind of inference or something. And U is a cover of Y. When we say U is a cover of Y, we're saying that U captures everything in Y plus a little more. And then we can specify that. We can refine that cover. So it's kind of like we made a good first try, and then we can kind of slowly approach.
Like V is the restricted version of U over Y, right? Like
Yeah.
approximates Y better than U, in a sense.
Exactly.
Yeah, I think another good analogy, it could be like making an argument precise, right? It's making
Yeah.
it apply more, it's localizing each one of the pieces of it.
Yeah.
Is this related to the atoms in a way, like to the whole component discussion, right? We were talking about
components.
the move from components to atoms, a sort of similar refinement.
Yeah, I was thinking about that. That
think you're
atom
right.
is a atom is a refinement of phenomenal component.
And it's nice because it does give you, let's say, the fact that you can move from the logical and the topological. You can see that this refinement on covers is like finding the right resolution to have the greater the bound that is the closest to the thing being covered, right? And logically, it concerns, let's say, finding the predicates that describe only that and not more stuff, right?
Yeah.
It's not just any refinement; it's a specific refinement that like localizes it.
Yeah, exactly. So, but the crazy thing is that since you can have this dual description of spatial and logical, you see that finding the right, let's say, descriptive resolution for the predicates so that they only capture what you're interested is like defining what is the let's say the sort of covering that defines what is a localization in that space, right? Not only simply finding the localization, but defining it.
Yeah, because once you have found the atom, you can then localize to create other points, basically. I think the difference between this picture here and what we're just saying is that I think here Y would have to be a single point, right? So because, and this maybe is related to the notion of a localic. Again, we can have covers of this Y, which are like this, right? This is a cover and contains more points than Y. And then we have another cover, which is even bigger than this one, right? With some points.
I think at the level of atoms, we don't need this to be a point, right? Only the real atoms mean that if you define a certain covering, right, this minimal covering, then it correlates something in the multiple, like an element in the multiple. But I think at the atomic level, that I'm not sure if that's, I mean, it needs to be unique with regards to the logical space, not with regards to the singling out of an element in a multiple, right?
Even real atom doesn't have to be a point.
Yeah, I mean, technically, real atom is just a multiple, right?
Yeah.
But yeah, I mean, whether it's 1 point or multiple, it doesn't
really
matter.
Yeah.
Yeah,
Even
but
in this example, that doesn't matter.
Yeah, and we should strive actually to think of these things not as like the point-free definition of these things, right? So again,
especially because I think that also, I mean, it's not simply to think without points, but when you start without points, you get to define what counts as a point, right? I think that's also the important thing. I mean, there is a logical constraint on what counts as a point. It's not an ontological one, right? There will be a correlation between the two, let's say multiples and what works as this minimal atomicity, right? But this is given by the logic and not prescribed by the ontology, right?
Yeah.
Actually, part of my, I had a little bit of trouble basically not being bogged down by the terminology of atom and stuff like that. Now, looking at this and basically thinking of points as open sets, I think it is a lot better, and it basically does for me what I had to do on my own in order to think of atom of something that is not a point in Badiou's usage of this term. As a matter of fact, everything that we encounter in logics of word are basically open sets.
Yeah.
We just say that there are particular open sets that are prescribed by real elements, and we call them real atoms.
Yes, but an atom is
that's a better approach.
Yeah, that's good.
But I do think that the idea of atoms is good in the sense of this. I mean, he does want to connect what he's doing to a tradition of, let's say, to almost like a consummation of an atomist project, right? Where it starts to make some sense to talk about what was a metaphysical sort of mythical idea of atoms and void. It does make some sense in his theory.
Yeah, I did want to, I had an idea, a visual representation of atoms that I wanted to run by you guys. I can, I guess, do that since we're almost out of time, but I think we can consider atoms as being the center of some world. Not world is the wrong term, but let's say the center of some field of objects. And let's say A is the atom, right? It can be an open set, not a point, right? And then the way that it measures. So again, this is to use the distance, the metric metaphor, rather than the partial set, right? So we know that that identity measures this in some sense. Identity measures, if this is a point Q, and this is A comma Q, right? And then let's say that's equal to like,
right?
Sorry, what?
In an inverse way, because ID AA is going to be maximal.
Yeah. Right. So inversely. So yeah, and actually we know that ID AA is not necessarily maximal. It's the existence of A, which can be less than M.
Well, within the atom of A. It's
within the atom. Okay, within the atom, let's say it's max. Yeah, this was actually a big debate we had about whether IDAA is the same as EA is the same as alpha of A. Okay, let's say for now that identity of AA is maximal. right? And then it goes outward. So 2 points are on the same orbit if they're not related to each other, right? So we know that degrees, like degree, I shouldn't have used Q. Let's say degree
B.
Yeah, B, right? Or let's call this B, and let's call this C, right? And then the distance from A to B is Q. And let's say the distance in the sense of identity again is P. If Q and P do not have a relation, in other words, if P and Q is the minimal, right? Then we can say they belong in the same orbit. So in that sense, every atom defines these concentric circles of all the other multiples.
Sorry, if P and Q have nothing in common, then B and C are on the same orbit.
Yeah. Right. We say that you're on a different orbit if your degree relative to A is related in some way, right? So the distance from, this is a way to generalize distance.
Yeah, but this relation wouldn't be transitive, right? Of these like orbits. You can have two things, A and B, that are close together, that are comparable, that are both not individually comparable to some other C.
Well, because partial orders are transitive.
No, but I'm saying that this relation of being on this orbit isn't transitive, right? Of having minimal, or of being not comparable to one another.
Oh, so you're saying P and Q are not comparable, but P might be comparable to something else?
Yeah.
But then I think, so let's say P is less than Z, and you're saying P
Q that's less than P, but that's also
P is less than C, and P and Q are unrelated. So
okay.
I don't know the sign for not related, but say just like,
sure,
right? And you're saying,
yeah, you can have P not related to Q and Z not related to Q, but P and Z related. Yeah.
Yeah.
That's possible.
I see. And then Q would then, Z would then be on an orbit. Q, okay.
I'm just saying that it just means that this idea of being not comparable is not an equivalence relation.
It doesn't guarantee that they are in the same orbit. It's not enough to describe things in the same orbit, right?
Yeah.
Yeah, I see what you're saying.
But there is a way to think about this. You can think about things that are not comparable, and then they're like eventually meet to be comparable potentially.
Yeah, this is.
But going back to
we need to collapse it somehow. But yeah, go ahead.
So the idea of being on an orbit is that all the degrees that are unrelated will be on the same orbit, and all the degrees that are related will be on a line.
Mm-hmm. No, all the degrees. Yeah. What do you mean by line?
Oh, I mean, like for example, let me get this annotation thing.
Yeah, A, B, and D. There is
so
kind of
in this
order.
case, then.
Oh yes, yeah.
Z would be somewhere here. So P is in this, since P is related to Z or Z, then they should be comparable in this way. Whereas everything that is around this are not comparable at all. We don't know the relation of this line and this line, but we know the relation of this line and this line.
Yeah, that's what I was trying to say. Yeah. Yeah, exactly. So you have a kind of lines going outward like this.
Right.
And these lines are ordered chains
Right.
in
So these are the chains of the lattice, whereas
yeah,
this
is
actually
here.
This is a brilliant way to show related and
So-
non-related stuff in a lattice.
Yeah. So here, the orbits would be like this, right? Kind of, right, and so on.
No. A, C, D. Well, A cannot be in the same orbit as E, D, and C. So the orbit does not go through A.
It doesn't go through A. Yeah, sorry.
Okay, all right.
Then
Okay.
The A is kind of in the center, let's say.
I think you just invented a notation for lattices, an additional notation.
Yeah, well, if we can solve the issue that Yasha showed us, which is this.
Yeah, but isn't actually the two conditions, right? They must be P and Q, the conjunction is minimal, but they're both enveloped by something that is further out, right?
Mm-hmm. Yes.
Yeah.
And the combination of the two gives you, let's say, allows you to define perhaps with some extra information there that they are on the same strata of distance, right?
Mm-hmm.
Yeah, you can define these strata as like cochain covers.
Mm-hmm.
You know, Dennis?
Yeah.
So sets are all have mutually non-compatible elements. That's like different slices of the Heyting algebra. But there's different ways you could slice that.
Mm-hmm.
And that would be like the different like resolutions of it, I guess.
Yeah. I actually got this idea from thinking through the idea of a Grothendieck topology, which is how you turn a category into a topological space, or something like a topological space. And I think that's related to what you're saying, Yasha, in a way, because you have maps that go, or morphisms that target a specific object. And if you create a certain condition on those morphisms, you get a topological space. You treat that object as if it were the top of a lattice.
Yeah, I think that
here is
right?
monomorphisms.
Yeah.
What's helping you here is that
Mm-hmm.
Dennis, if I understood it correctly, is that the way you define this distance, it actually is something that supports compatibility, right? Because localize A on B and B on A is the same, right?
Yeah.
This kind of intuitive idea of distance. So now you define, let's say, strata of localization, right?
Exactly. Stratas of localization with respect to A.
Yeah.
Yeah, so I had this idea for an app, actually, like a little animated app. So imagine you have a space of a bunch of points.
Reza, could you delete just in your
I'm trying to delete it. Clear? Okay, great.
Imagine you have a space of points. They're just free-floating points, and you choose one to be your privilege point here. And let's say this little app, you can click on this point. You then animate it so that all other points fall into an orbit around A.
I actually have that app. It's called, where is it?
It already exists.
It's called Earth Editor.
That's amazing.
Here, and I won't be able to show you guys, but if you can create something, look, it goes into orbit. In this case, it's attracting to something central, but.
Yes, yeah.
That's fun.
Exactly.
Like
exactly.
Black hole.
Yeah, in this case, I created something that is not stable, but.
Yeah, so you have these free-floating points. You click one, and then suddenly all the other points move into an orbit, and then they rotate around that point. But let's say you choose another point. Suddenly, all the other points, including A, will move again to form a new set of orbits around this, right?
Mm-hmm.
And this gives us a way to think about real synthesis and compatibility and localization in terms of which two of these are consistent viewpoints of the orbits, right? Because we could say localization or compatibility means that things that fall into one orbit, like the things that fall into the closest orbit on A, also must fall into a certain orbit on B, if A and B are compatible.
Yeah.
Something like that. Yeah. I don't know how to make that precise, but I think that's the intuition.
But you understand that orbits cross, right?
Orbits cross.
Orbits must cross. Unless I misunderstood what the condition of making an orbit. You say what is on an orbit is when their conjunction is minimum, right? So
yeah.
So in your example, Z and P are not on the same orbit because there is a partial order between them. Whereas Q and Z are non-related. So P, there is an orbit that includes Z and Q, and there is an orbit that includes P and Q.
Yeah.
I don't understand that. I thought,
you're saying
I thought Z as the furthest point is just all the elements, all the values Q, P, and so on that define distances that are the same distance from A, but are incomparable between them, and that are smaller than some upper bound like Z. They will be on the same.
You cannot use the same distance and incomparable, right? Because if they are same instance, they are comparable.
Yeah, so they may not be comparable, but they like someone said earlier, they might have a common parent. No,
I think that if they are compatible, let's say if A is compatible with B to P degree, and no, that is not enough. I would say, and if it's also compatible with C to the P degree, that's not enough.
Yeah. So the definition, if the definition of orbit is that a degree P and a degree Q. Wow, this is so hard to write. Are not related.
That's one of the conditions, not the only one though.
Okay, what is the other?
The other one is they must share a common.
Their orbit smaller than a bigger order, right?
Yeah, they have they have a certain what's it called? Their join.
Their what?
Their envelope. They must share a common envelope, no?
No, I think it's just that the envelope is something that's included in your greater set that both of these things are in.
Yeah. So does it mean the orbits are envelopes of elements?
In the language of lattice, they have a common join, but no meets. They have one join at least.
Mm-hmm. Yeah, let's just think about it this way. Like, can we group them because B, C, and D have the same envelope, their lowest upper bound, right? LUB of BCD is A.
Correct.
The lowest upper bound of IJ is D, but then so then D must be less than A. But then G and H, their lowest upper bound is C. And C is less than A. I don't know if that reproduces the problem again, but.
I mean, in each one of these, the envelope of it is not going to be contained within it.
I mean, isn't the way Badiou works through the transcendental functor kind of a different way to discuss this? Because he says, well, let's have this functor for the degree P that only selects stuff with degree P. Isn't it like selecting everything that has p distance from A, for example.
Yeah, it's that is
So,
p
yeah.
distance, but the question is, can we picture that p distance in a consistent way on a two-dimensional surface, right? Because p distance and q distance are not related. So how do you show both p and q distance?
But we're talking about orbits that have like spherical forms, right, or circular forms, right? We're not talking about orbits with, you define them based on a precise distance, right?
Yeah.
Then I think the problem is that then you define 2 points that are not the same, but they have the same distance, and you wanted this not same to be explicitly defined, but to say all the points that have p distance from A, that's already a definition.
Yeah.
Every other point which has q distance from A, which is not p, will give us a different.
Yeah. So we already talked about this actually with the whole thing about monotonic maps, right? We can do this.
Yeah.
Just the collapsing, and these are the orbits.
Yeah.
Yeah.
Yeah. I gotta go, guys.
Yeah, me too.
Yeah, I think it's a good place to end.
Yeah.
No, but this was amazing.
You're good.
Yeah, I really think that the
Thanks,
point
guys.
where you stopped with this idea of defining these orbits and talking about atoms and coverings, I mean, it's a nice kind of thing to explore a bit further, because it's clear that the transcendental functor scholium is where the more topological, like, since we're moving from the transcendental back to the world, it's where this idea of, seeing the logic in the topology, right, seems to come into play. So this idea that coverings, atoms, they are related, seems to be a more constructive way to approach all of that, So perhaps it would be something nice to talk about more.
Yeah.
So for the next session, just a question: are we finishing this? You think that it will take the whole session, or are you assigning reading from the relations book, or you want to think about it and let us know?
Yeah. So I'm actually only halfway through the presentation, but I think a good source of reading, if you have time, is to read the beginning of that 7 Sketches book.
Okay. Can you specify the pages? Because I know nothing about category theory, so I finally going through various different sources, I decided to go back to Mathematics of Transcendental, the first part. I think that would be good, although it does not talk about a lot of things in category theory. There is no reference of sheaves and stuff like that in that. I thought it is better because it is simple, and it is like, I'm hoping that it takes me right to the point where Badiou is focusing. And besides, it is just a summary. It's much faster to go through that than going through the Golden Blot, like 400 pages.
Yeah,
summary of Golden Blot
gives you the minimum of what you need.
Yeah.
Dennis, I think that you should just make a decision. I mean, personally, I'd be up for finishing a presentation next week if you want, or perhaps doing an added meeting next week to have both, one meeting on the book and one meeting to finish the presentation. So whatever you want, but I think that, how are you with the relation chapter presentation? Like, do you want more time to prepare? Could you do it next week anyway?
Yeah, I need more time on that anyway.
So perhaps it's better to have another week on this.
I agree. Let's go through this. This was such a good presentation.
Yeah, I think so.
Thanks, man. Yeah, you guys helped me a lot with understanding it myself. It's a lot to let sink in, especially because every concept in math seems to just spiral out into a million other variations, you know. So
Yeah,
being able to like travel
all-
together through it is helpful.
they were all sort of independent,
Mhm.
like different types of math, and then they all got unified later. So
Exactly. Yeah, that's the
all
hard
these
part.
different
Is
versions, yeah.
yeah, how do you
So,
coherently unify all this stuff?
If you want to assign us the reading, like if you share this and also assign us a reading of whatever source, that would be great, Dennis.
Yeah, I have a few texts that I think would be really helpful, especially because I'm learning from them right now too. So it would
Sounds
help a
good.
lot to get a second eye on it.
Sounds good.
Great, guys. Thanks for attending.
Thanks.
Excellent work, Dennis.
Thank you.
Was amazing.
Really enjoyed it. It was good to see you guys.
Good to see you too. See you
Take
guys
care.
next week.
See you.
Take care, guys.
Bye-bye.
Bye.